Tonight, we're going to take a journey that stretches across billions of years of cosmic history. We're going to explore the scars on the face of our nearest celestial neighbor, and in doing so, we're going to unlock secrets about the very origins of our solar system. We're going to talk about lunar craters, and by the end of this journey, you'll never look at the moon the same way again. Before we begin, if you enjoy these deep, relaxing explorations of the cosmos, a quick like or subscribe would genuinely help the channel grow. Now, let's step outside together. Look up at that pale, luminous disk hanging in the night sky and begin to understand what it's really showing us. On any clear night, the moon dominates the sky in a way no other celestial object can. It's close enough that you can see detail with your naked eye, and if you look carefully, you'll notice something immediately. The surface isn't smooth. It isn't uniform. There are bright regions and dark regions, rough patches and smooth plains, and scattered across nearly every part of the visible face, there are circles, thousands upon thousands of circles of every conceivable size. Some are so large they define the moon's very appearance. Others are so small they're invisible without a telescope. These circles are craters, and each one tells a story. A lunar crater is a depression in the moon's surface, formed when an object from space, an asteroid, a meteoroid, a fragment of a comet, struck the surface at tremendous speed. The physics of these collisions are extraordinary, involving energies that dwarf anything in human experience. But the result is deceptively simple in appearance. A bowl, a ring, a scar pressed into ancient rock. And because the moon has no atmosphere to erode them, no liquid water to wash them away, no tectonic plates to recycle the crust, these scars endure. Some of the craters you can see tonight formed over 4 billion years ago, when the solar system was young and violent and chaotic. They've been sitting there, virtually unchanged ever since. This is what makes the moon so profoundly valuable to science. It's a record keeper. Earth has a similar history of bombardment, but our planet's restless geology has erased almost all evidence of it. Plate tectonics subduct old crust into the mantle. Wind and water and ice gnaw relentlessly at the surface. Volcanoes resurface entire regions. The oldest rocks on Earth's surface are only about 4.28 billion years old, and most are far younger, but the moon preserved what Earth could not. Its surface is a library, written in stone and dust and shadow, containing chapters from the earliest days of our solar system's existence. The craters are the words, and scientists have been learning to read them for centuries. The story of our understanding of lunar craters begins, fittingly, with Galileo Galilei. In late 1609, Galileo built one of the first practical telescopes and turned it toward the moon. What he saw overturned centuries of philosophical assumption. The moon, which Aristotle and generations of thinkers after him had declared to be a perfect celestial sphere, was nothing of the sort. Its surface was rugged, mountainous, pitted with depressions. Galileo sketched what he saw, capturing the interplay of light and shadow along the boundary between the moon's lit and dark halves, the region astronomers call the terminator. Along this line, the low angle of sunlight throws every surface feature into dramatic relief. Mountains cast long shadows, crater rims gleam like bright rings, and the floors of deep craters lie in total darkness. Galileo didn't know what had caused these depressions. Neither did Johann Hieronymus Schröter, the German astronomer who, in 1791, first applied the word crater to them, borrowing a Greek term meaning vessel or bowl. For a very long time, the prevailing explanation was volcanic. Robert Hooke, in his landmark 1665 work, Micrographia, proposed two competing hypotheses. One suggested the craters were caused by projectile bombardment from space. The other attributed them to volcanic activity, like bubbles rising in boiling mud. The volcanic theory held sway for centuries, partly because volcanism was a familiar terrestrial process, and partly because the alternative rocks falling from the sky seemed far-fetched to many serious thinkers. But the volcanic explanation had problems. Observers as far back as the late 18th century pointed out that most lunar craters were far larger than any volcanic feature known on Earth. The shapes were wrong too. Volcanic calderas typically have irregular outlines and are associated with constructive features like cones and domes. Lunar craters were overwhelmingly circular, regardless of size, and they were associated with destructive features, with excavation and disruption of the surrounding terrain. The scientific debate continued for well over a century. In 1893, the American geologist Grove Carl Gilbert made a compelling case that the lunar craters were formed by impacts from large objects. But his ideas were largely ignored. It wasn't until the mid-20th century that the impact theory began to gain real traction, driven largely by the work of one remarkable scientist. Eugene Shoemaker, a geologist who would become one of the most important figures in planetary science, studied Meteor Crater in Arizona during the late 1950s and early 1960s. This kilometer-wide hole in the desert floor had been formed approximately 50,000 years ago by the impact of an iron meteorite. Shoemaker found minerals in the crater rocks that could only form under the extreme pressures generated by hypervelocity impact. He demonstrated conclusively that Meteor Crater was an impact structure, and then he looked at the moon and recognized the same physics at work on a vastly larger scale. Shoemaker essentially founded the discipline of planetary geology. He trained Apollo astronauts in field geology. He mapped lunar stratigraphy, developing systems for determining the relative ages of different lunar surfaces based on which features overlapped which. His work transformed lunar craters from curiosities into scientific tools, instruments for reading the history of the solar system. And that history, as we're about to discover, is far more dramatic and violent than anyone had imagined. To understand lunar craters, we first need to understand the moon itself, where it came from, how it formed, and why its surface became the canvas upon which billions of years of cosmic violence would be recorded. The leading scientific explanation for the moon's origin is called the giant impact hypothesis, and it describes one of the most cataclysmic events in Earth's history. Approximately 4.5 billion years ago, when the solar system was still in its infancy, the young Earth was struck by another planetary body. This impactor, which scientists have named Theia, after the Titan of Greek mythology, who was the mother of the moon goddess Selene, was roughly the size of Mars. It was a world in its own right, with its own iron core and rocky mantle, and it collided with Earth at an oblique angle, at speeds of perhaps 4 kilometers per second or more. The energy of this collision is almost beyond comprehension. The impact vaporized a significant portion of both Earth's outer layers and Theia itself. Immense quantities of molten rock, superheated vapor, and shattered debris were blasted into orbit around the battered Earth. Some of Theia's iron core merged with Earth's core, which is one reason our planet has the highest density of any planet in the solar system. But the lighter silicate material, the mantle rock from both Earth and Theia, formed a vast ring of debris orbiting the wounded planet. Within this debris ring, gravity went to work. Particles collided, stuck together, and gradually accumulated mass. Computer simulations suggest that the Moon may have coalesced remarkably quickly, perhaps in a matter of hours, according to some recent models from NASA's Ames Research Center, though other models suggest a longer process, taking months or years. Either way, the result was the same. A new world was born, assembled from the wreckage of a planetary collision. This new world was the Moon. The evidence for this violent birth is extensive and compelling. Apollo mission samples showed that the oxygen isotope ratios in lunar rocks are virtually identical to those in Earth's mantle, indicating a shared origin. The Moon is significantly depleted in volatile elements, substances that evaporate easily at high temperatures. Exactly what you would expect if the material had been through a catastrophic heating event. The Moon has a much smaller iron core relative to its size compared to Earth, consistent with the idea that Theia's core merged with Earth's rather than contributing to the Moon. And the Moon's bulk composition, its mixture of minerals and elements, is remarkably similar to Earth's mantle material, supporting the idea that the Moon formed primarily from the outer layers of both bodies. When the newly formed Moon coalesced from this orbiting debris, it was extraordinarily hot. The energy of accretion, the constant bombardment of incoming material, adding to the growing body, kept the surface molten. The Moon was covered in what scientists call a magma ocean, a global sea of liquid rock hundreds of kilometers deep. This magma ocean was fundamental in shaping the Moon we see today. As the magma ocean cooled, minerals began to crystallize within it. Denser minerals rich in iron and magnesium crystallized first and sank toward the interior, eventually forming the Moon's mantle. But lighter minerals, particularly a calcium-rich feldspar called plagioclase, crystallized and floated to the surface, like ice forming on a pond. Over tens of millions to hundreds of millions of years, this floating plagioclase accumulated into a thick, light-colored crust. This crust, composed primarily of a rock type, called an orthosite, became the lunar highlands, the bright, heavily cratered regions that dominate the Moon's appearance. The oldest moon rocks brought back by the Apollo astronauts, and orthosite samples from the highlands, have been dated to approximately 4.4 to 4.5 billion years old, making them essentially as old as the Moon itself. These rocks preserve a record of that primordial crystallization process, a memory of the magma ocean's final cooling. The Apollo 16 mission, which landed in the Descartes Highlands, recovered some of the oldest and most scientifically important of these samples. One, an orthosite specimen, sample 60,025, has yielded ages ranging from approximately 4.36 to 4.44 billion years, depending on the dating method and study, with recent research suggesting the sample is actually a complex mixture of differently sourced materials whose full history is still being unraveled. Even at the younger end of that range, when you hold such a rock, you're holding something that solidified from molten magma within roughly 200 million years of the solar system's formation. It is older than almost anything on Earth's surface. As the crust solidified and the magma ocean cooled beneath it, the moon's surface became a blank canvas, pristine, unmarked, a fresh world waiting for the universe to write upon it. And the universe was about to write with tremendous violence, because the early solar system was not the orderly, well-swept place it is today. It was a shooting gallery, filled with the leftover debris of planetary formation. Planetesimals, the building blocks that hadn't been incorporated into planets, wandered on chaotic orbits. Asteroids, comets, and fragments of all sizes careened through the inner solar system. And the moon, a new and defenseless world with no atmosphere to shield it, sat squarely in the path of this onslaught. The bombardment began almost immediately after the crust solidified, and it would continue with varying intensity for billions of years. The record of that bombardment is written in every crater on the moon's surface, every depression, every ring of raised rock, every splash of bright ejecta tells a story of a moment when something from the depths of space arrived at tremendous speed and transformed a patch of lunar landscape forever. To truly appreciate what the craters tell us, we need to understand how they form. The physics of impact cratering is one of the most dramatic processes in all of planetary science, and it happens with breathtaking speed. An impact that creates a crater 100 kilometers across, a process that excavates millions of cubic kilometers of rock and reshapes the landscape for hundreds of kilometers in every direction, is over in a matter of minutes. The geological consequences persist for billions of years, but the event itself is almost instantaneous. Let's walk through what happens when an asteroid strikes the moon, step by step. Imagine an asteroid, perhaps 10 kilometers in diameter, a rock the size of a small mountain, approaching the moon on a collision course. It's traveling at a typical impact velocity for objects in the inner solar system, somewhere between 15 and 25 kilometers per second. At the lower end of that range, 15 kilometers per second, the object is moving at roughly 54,000 kilometers per hour. That's fast enough to cross the entire continental United States in about 5 minutes. At 25 kilometers per second, it would make that same crossing in about 3 minutes. When this object contacts the lunar surface, something remarkable happens. At these speeds, the impactor doesn't push the ground out of the way like a ball landing in sand. Instead, the kinetic energy of the impact is so enormous that it behaves like an explosion. The impactor and the target rock are both instantaneously subjected to pressures millions of times greater than atmospheric pressure on Earth. These pressures vastly exceed the structural strength of any known material. The rock doesn't merely break, it's compressed, pulverized, and partially vaporized. A tremendous shock wave radiates outward from the point of impact, moving through the lunar rock at speeds of several kilometers per second. This is the excavation phase of crater formation. The shock wave compresses the rock ahead of it, and as it passes, the rock decompresses explosively. This decompression drives the material outward and upward, excavating a cavity in the surface. The process works in all directions simultaneously, which is why impact craters are almost always circular, regardless of the angle at which the impactor arrived. Even a very oblique impact, one coming in at a shallow angle, produces a roughly circular crater. You only start to get noticeably elongated craters at extremely shallow angles, below about 15 degrees from horizontal. The excavated material, called ejecta, is launched outward on ballistic trajectories. Some of it is hurled at high velocities and lands far from the crater, forming a widespread ejecta blanket. Closer to the crater, the ejecta is thicker and more continuous. The largest fragments can themselves strike the surface with enough force to create smaller secondary craters, which often appear in chains or clusters radiating away from the primary crater. Some ejecta is thrown so fast that it achieves escape velocity and leaves the moon entirely. A fraction of this material eventually falls to Earth as lunar meteorites, fragments of the moon that scientists have found in deserts or ice fields around our planet. As the excavation phase concludes, the modification phase begins. For small craters, less than about 10 to 15 kilometers in diameter on the moon, modification is minimal. The result is a simple crater, a clean bowl shape with a smooth, concave floor and a raised rim. These look exactly like what you might picture if someone asked you to draw a crater. LUNAR crater, a young and beautifully preserved simple crater only 2.2 kilometers across and thought to be less than 10 million years old, is a textbook example. But for larger impacts, the modification phase is dramatic and complex. When the excavated cavity reaches a certain size, the walls become unstable. They collapse inward in a series of enormous landslides, creating a terraced inner wall that descends to the crater floor in a series of steps. Meanwhile, the floor of the crater rebounds upward. The deep rock beneath the initial cavity, momentarily compressed by the impact, springs back, pushing material up from the center of the floor. The result is a central peak, a mountain or cluster of mountains rising from the center of the crater floor. These central peaks are composed of material that has been uplifted from considerable depth, sometimes from kilometers beneath the original surface. They offer scientists a window into the moon's subsurface, geology without having to dig. Craters with these features, the terraced walls, the flat floors, and the central peaks, are called complex craters. They represent the majority of large craters on the moon. Copernicus crater, 93 kilometers in diameter and one of the moon's most visually spectacular features, is a classic complex crater. When you look at it through even a modest telescope, you can see the terraced walls, the cluster of central peaks, rising roughly 1.2 kilometers above the crater floor, and the extensive ejecta blanket spreading outward from the rim. Even larger impacts create structures called multi-ring basins. When the impactor is large enough and energetic enough, the crater's formation affects such a vast area that multiple concentric rings of mountainous terrain form around the central depression. The Oriental Basin, one of the youngest large basins on the moon at approximately 3.8 billion years old, is the best preserved example. Its outermost ring, the Cordillera Mountains, stretches approximately 930 kilometers from east to west. Inside this outer ring are additional concentric rings of mountains with a relatively flat interior basin at the center. Oriental sits on the moon's western limb, on the boundary between the near side and far side, and can only be glimpsed from Earth when conditions of libration, the slight wobbling of the moon as it orbits, tilt it slightly toward us. The energy involved in creating these enormous basins is staggering. The impact that formed the Imbrium Basin, one of the largest and most prominent features on the moon's near side, released energy equivalent to billions of nuclear weapons, detonating simultaneously. The impactor was estimated to be roughly 250 kilometers in diameter, a body the size of a small dwarf planet. The collision excavated millions of cubic kilometers of lunar crust and mantle, blasted ejecta across nearly the entire visible face of the moon, and sent shockwaves through the moon's interior powerful enough to cause disruption on the opposite side of the globe. The formation of Imbrium was one of the most violent events in the moon's history, and its consequences shaped the lunar landscape in ways that are visible to the naked eye today. The ray systems associated with younger craters are among the most visually striking features of the lunar surface. When a crater forms, the ejecta that lands on the surrounding terrain is fresh and bright, not yet darkened by the gradual processes that affect the lunar surface over time. These processes, collectively called space weathering, include bombardment by micrometeorites, exposure to solar wind particles, and irradiation by cosmic rays. Over hundreds of millions of years, space weathering darkens the lunar surface, giving it the familiar gray appearance. But fresh ejecta hasn't had time to darken yet, so it appears brighter than its surroundings. The result is a system of bright streaks, or rays, radiating outward from the crater like the spokes of a wheel. The crater Tycho, located in the southern highlands, has the most spectacular ray system on the moon. Tycho is relatively young by lunar standards, approximately 108 million years old, based on analysis of samples linked to its ejecta at the Apollo 17 landing site. Its rays extend for over 1,500 kilometers across the lunar surface, reaching as far as the Apollo 17 landing site in the Taurus Littrow Valley, some 2,000 kilometers from the crater. At full moon, Tycho's rays are easily visible to the naked eye, appearing as bright lines radiating from a prominent bright point in the southern highlands. The persistence or absence of rays is one of the tools scientists use to determine relative ages of craters. A crater with bright rays is young. A crater with no visible rays but otherwise sharp features is middle-aged. And a crater that has been degraded by subsequent impacts, with softened rims and a floor partially filled with debris, is old. Eugene Shoemaker and his colleague Robert Hackman developed this relative dating system in the 1960s, using it to establish the basic stratigraphy of the moon. They defined 3 major time periods, named after representative craters. The Copernican period, the youngest, is characterized by craters that still have visible rays. The Eratosthenian period represents middle-aged craters with sharp features, but no rays. The name comes from the crater Eratosthenes, which sits just east of Copernicus and looks very similar in terms of freshness, but lacks rays, indicating it's older. And the pre-Imbrian period encompasses the most ancient surfaces, those that formed before the Imbrium impact, roughly 3.85 billion years ago. This stratigraphic system was a breakthrough. Before it, scientists had no reliable way to organize lunar history. With it, they could read the sequence of events preserved on the surface. Which crater came first? Which lava flow buried which crater? Which ejecta blanket covered which surface? The moon's history was suddenly decipherable, written in overlapping layers of impact, debris, and volcanic rock, waiting to be read by anyone who understood the language. Understanding the physics of crater formation also helps explain features that might otherwise seem puzzling. Why are all craters circular, even though impactors arrive from all directions at all angles? because the impact energy is so enormous that it overwhelms the directionality of the incoming object. The shock wave radiates equally in all directions from the point of impact, excavating a circular cavity regardless of the impactor's trajectory. Why do larger craters have flat floors while smaller ones have bowl shapes? Because the rock beneath large craters rebounds after the impact, partially filling the cavity and creating a flat floor, while in small craters, the forces involved aren't sufficient to cause significant rebound. Why do some craters have central peaks while others don't? Because central peaks form from the rebound of deeply compressed rock, a process that only occurs in impacts above a certain energy threshold. Each of these features contains information. The size of a crater tells scientists about the energy of the impact, which in turn reveals information about the size and speed of the impactor. The depth to diameter ratio tells them about the properties of the target material, whether it was solid rock or loose regolith. The morphology of the ejecta blanket can reveal whether water or ice was present in the subsurface at the time of impact, a phenomenon well studied on Mars, where Lobat ejecta patterns suggest subsurface ice. And the degree of degradation, how much the crater has been worn down by subsequent impacts, provides clues about its age. The moon's regolith, the layer of loose, fragmented material covering the bedrock, is itself a product of impact cratering. Over billions of years, the relentless rain of meteorites of all sizes has shattered ground and churned the surface, creating a blanket of pulverized rock and glassy beads, typically 2 to 20 meters thick. The regolith is a fascinating substance in its own right. It contains tiny glass spheres formed when impact melted rock was ejected and cooled in flight. It contains microscopic craters on individual rock grains, called zap pits, formed by the impact of tiny particles moving at extreme velocities. It preserves chemical signatures of the solar wind, trapped in the surfaces of individual grains over billions of years of exposure. And it records in its layered structure a timeline of the impacts that created it. Astronaut Buzz Aldrin's famous boot print in the regolith at Tranquility Base demonstrated its fine-grained, cohesive character. That boot print, undisturbed by wind or water, will remain visible for millions of years. Now that we understand how individual craters form, let's zoom out and look at the bigger picture. The history of bombardment on the moon isn't uniform. The rate at which impacts occurred has changed dramatically over time, and understanding these changes reveals some of the most important and hotly debated stories in all of planetary science. In the earliest days of the solar system, immediately following the moon's formation and the solidification of its crust, the rate of bombardment was extremely high. The inner solar system was still full of leftover material from the planet-building process, planetesimals that hadn't been incorporated into Mercury, Venus, Earth, or Mars. These objects, ranging in size from pebbles to small moons, orbited the Sun on chaotic trajectories that frequently intersected the paths of the newly formed planets and their satellites. The Moon, Earth, and all the other inner solar system bodies were subjected to a fierce and sustained rain of impacts. This early period of intense bombardment is recorded in the Moon's heavily cratered highlands. When you look at the bright regions of the Moon, those ancient highland surfaces saturated with overlapping craters, you're seeing the result of that early onslaught. The crater density in the highlands is extraordinary. Craters overlap other craters, which in turn overlap still older craters. Some regions are so densely cratered that virtually every square kilometer has been hit multiple times. The cumulative effect is a chaotic, rough terrain that looks utterly different from the smoother, younger Maria. But within this story of declining bombardment, there is a controversial chapter. In the 1970s, when scientists began analyzing the rock samples brought back by the Apollo missions, they noticed something unexpected: the radiometric ages of impact melt rocks. Material that had been melted by the energy of impacts and then resolidified seemed to cluster around a narrow time interval. Many samples from different Apollo landing sites, which were near different large impact basins, yielded ages of roughly 3.8 to 4.0 billion years. Very few samples showed impact, ages older than about 4.1 billion years. This apparent clustering led to a bold hypothesis. Perhaps there wasn't a gradual decline in bombardment after the moon formed. Perhaps the bombardment rate actually dropped off relatively quickly after the initial accretion period, and then spiked dramatically around 3.9 billion years ago, producing a sudden pulse of massive impacts. This hypothetical event became known as the Late Heavy Bombardment, or sometimes the Lunar Cataclysm. The idea was first proposed by Fuad Terra, Dimitri Papanastasiou, and Gerald Wasserberg at Caltech in 1974, based on their analysis of Apollo samples. If the Late Heavy Bombardment actually occurred, it would have been a catastrophic event. During a relatively brief geological interval, perhaps 200 million years, the Moon, Earth, and all the other inner solar system bodies would have been pummeled by a massive influx of asteroids and comets. On the Moon, this bombardment would have created most of the large impact basins we see today, including Imbrium, Serenitatis, and Nectaris. On Earth, the effects would have been even more devastating. Extrapolating from the lunar crater record, scientists estimate that if the late heavy bombardment occurred, Earth would have experienced over 22,000 impacts, creating craters larger than 20 kilometers in diameter, roughly 40 impacts, creating basins approximately 1,000 kilometers across, and several impacts, creating basins roughly 5,000 kilometers in diameter. The energy input would have been sufficient to sterilize Earth's surface multiple times over. But what could have caused such a sudden spike in impacts hundreds of millions of years after the planets formed? The most influential explanation came from a group of scientists working in Nice, France, and their theory has become known, naturally enough, as the Nice model. First published in a series of landmark papers in the journal Nature in 2005, the Nice model describes a dramatic episode of planetary migration in the outer solar system. According to the model, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, did not always occupy their current orbits. In the early solar system, they were packed much more tightly together, orbiting closer to the Sun and to each other. Beyond Neptune's original orbit lay a massive disk of icy planetesimals, remnants of the planet-building process, containing perhaps 30 to 50 times the mass of Earth. Gravitational interactions between the giant planets and this disk of planetesimals gradually caused the planets' orbits to evolve. Jupiter migrated slightly inward toward the Sun, while Saturn, Uranus, and Neptune migrated outward. At some point, Jupiter and Saturn crossed a critical orbital resonance, a configuration where Saturn completed one orbit for every 2 orbits of Jupiter. This 2-to-1 resonance triggered a cascade of gravitational chaos. The orbits of Uranus and Neptune became violently unstable. They may have been flung outward through the planetesimal disk, scattering billions of icy bodies in all directions. Some of these scattered objects were hurled into the inner solar system, where they rained down on the terrestrial planets and their moons. In some versions of the NIS model, a 5th giant planet, an additional ice giant similar to Uranus or Neptune, was originally present. This hypothetical planet was ejected from the solar system entirely during the instability, flung into interstellar space by a close encounter with Jupiter. Its departure helped explain how the remaining planets settled into their current, relatively stable orbits. The NIS model was elegant and powerful. It explained not only the late heavy bombardment, but also the current orbital structure of the outer solar system, the existence of the Kuiper Belt, the population of Jupiter's Trojan asteroids, and the irregular satellites of the giant planets. For years, it was the dominant framework for understanding early solar system dynamics. However, the story has grown more complicated over time. Beginning in the 2000s, several lines of evidence began to challenge both the idea of a sharp, late heavy bombardment and the timing proposed by the NIS model. More precise measurements of Apollo samples revealed tiny portions of rock with ages older than 4 billion years, suggesting that the apparent clustering of ages might be partly an artifact of sampling bias. All 6 Apollo landing sites were on the moon's near side, clustered in a relatively small region, and several were deliberately chosen for their proximity to major impact basins like Imbrium, Serenitatis, and Nectaris. It was plausible that many of the supposedly different impact melt samples all traced back to 1 or 2 massive events, particularly the Imbrium impact, which scattered ejecta across much of the near side. Furthermore, newer dynamical studies suggested that the planetesimal disk in the outer solar system would have dispersed within the first 100 million years of solar system history, far too early to trigger a bombardment at 3.9 billion years ago. This led some researchers to propose that the giant planet instability occurred much earlier, possibly simultaneous with the final stages of terrestrial planet formation. In this scenario, the heavy bombardment was a real event, but it wasn't late. It occurred within the first few 100 million years, and the bombardment that created the large lunar basins was primarily the tail end of a long, gradually declining reign of leftover planetesimals rather than a sudden spike. Recent research from 2023 and 2024, including a major study published in the journal Icarus, has shown that leftover planetesimals from the terrestrial planet zone, objects that formed in the same region as Mercury, Venus, Earth, and Mars, were likely the dominant source of impactors during the Moon's first billion years. This represents a notable shift from earlier theories that invoked the asteroid belt, comets, or scattered Kuiper Belt objects as the primary sources. The debate continues today, and it's one of the most active areas of research in planetary science. Was there a true cataclysmic spike in bombardment around 3.9 billion years ago? Or was the impact rate simply declining gradually from a very high initial level? The answer matters enormously, not just for understanding lunar history, but for understanding the conditions under which life first emerged on Earth. If the late heavy bombardment was a real concentrated event, it would have posed a severe challenge to any early life on our planet. If, on the other hand, the bombardment was more gradual and extended, the window for life's emergence may have been wider than previously thought. Future missions may help resolve this debate. Samples from the South Pole Aitken Basin, the Moon's oldest recognized impact structure, could provide crucial constraints on when the heaviest bombardment occurred. China's Chang'e 6 mission, which returned samples from within this basin in June 2024, has already begun to yield results. Analysis of norite clasts, a type of rock formed from impact melt, from the Chang'e 6 samples has identified 2 distinct impact events, one at 3.87 billion years ago, and another at 4.25 billion years ago. The older date is the best constraint yet on the age of the South Pole Aitken Basin impact itself, providing an anchor for the older end of the lunar crater chronology. As more samples are analyzed and as future missions return material from other key locations, the story of the Moon's bombardment history will continue to sharpen into focus. Among all the craters on the Moon, a handful stand so far above the rest in scale that they deserve special attention. These are the Great Basins, impact structures so enormous that they shaped the Moon's geography on a hemispheric level. Their formation represented some of the most violent events in the history of the inner solar system, and their legacies are visible to the naked eye every time you look up at the Moon on a clear night. Let's explore 3 of the most important. The South Pole Aitken Basin is, by most measures, the single most impressive impact structure in the entire solar system. Located on the Moon's far side, it stretches approximately 2,500 kilometers from outer rim to outer rim, roughly the distance from Washington, D.C. to Waco, Texas, or from London to Moscow. Its average depth is about 6 to 8 kilometers, reaching up to 13 kilometers in its deepest points, making it also the deepest known impact basin in the solar system. It is named for 2 features on opposite sides of its vast expanse: the lunar South Pole at one end and the small crater Aitken at the northern end. The existence of this colossal structure was suspected as early as 1962, based on early Soviet probe images from Luna 3 and Zond 3, but it was not confirmed until the mid-1960s, when the American Lunar Orbiter program returned wide-field photographs that allowed geologists to recognize its true size. Because it lies almost entirely on the far side, the South Pole Aitken Basin cannot be seen directly from Earth. You can catch the faintest suggestion of its mountainous outer rim on the Moon's southern limb, but the full extent of the structure is invisible from our vantage point. It took spacecraft orbiting the far side to reveal this hidden giant. The impactor that created the South Pole Aitken Basin was immense. Simulations suggest it may have been a body roughly 200 kilometers in diameter, striking at a relatively low angle, perhaps around 30 degrees from horizontal. The low angle of impact would explain several unusual properties of the basin, including the fact that it did not excavate as deeply into the lunar mantle as a vertical impact of that energy would have. Despite the enormous size of the structure, crustal thickness maps generated from the Grail mission's gravity data indicate that there is still approximately 10 to 16 kilometers of crustal material beneath the basin floor in undisturbed regions. This is unexpected for such a massive impact, and the oblique impact angle is the most widely accepted explanation for why the impactor didn't dig all the way through to the mantle. The age of the South Pole Aitken Basin has been one of the most sought-after numbers in planetary science. It is clearly the oldest recognizable basin on the Moon, predating all other major impact structures. For decades, scientists estimated its age at roughly 4.2 to 4.3 billion years based on indirect evidence, but direct confirmation required samples from within the basin itself. That confirmation finally came in 2024, when China's Chang'e 6 mission returned samples from the Apollo Basin, a smaller, younger crater located within the South Pole Aitken structure. Analysis of norite clasts, a type of rock formed from impact melt within the Chang'e 6. Samples identified 2 distinct impact events. One at 3.87 billion years ago, attributed to the formation of the Apollo Basin itself, and another at 4.25 billion years ago, interpreted as the best direct constraint yet on the age of the South Pole Aitken Basin impact. This finding places the basin's formation solidly in the earliest chapter of lunar history, roughly 250 million years after the Moon itself formed. But perhaps the most intriguing feature of the South Pole Aitken Basin lies not on its surface, but beneath it. In 2019, a team led by Peter James of Baylor University published a study in the journal Geophysical Research Letters, reporting the discovery of an anomalously dense mass buried deep beneath the basin's southern interior. Using gravity data from NASA's Grail mission combined with topography measurements from the Lunar Reconnaissance Orbiter, James and his colleagues detected an excess mass of at least 2.18 times 10 to the 18th power kilograms, extending to depths of more than 300 kilometers. To put that in more tangible terms, James described it as roughly equivalent to burying a pile of metal 5 times larger than Hawaii's Big Island beneath the surface. The dense mass is so heavy that it has physically depressed the basin floor downward by more than half a mile. What could this mysterious buried mass be? 2 leading hypotheses have emerged, though neither has been definitively confirmed. The first and most favored explanation is that it represents the metallic core of the impactor itself. When the object that created the South Pole Aitken Basin struck the Moon, the iron-nickel core of that body may not have been completely dispersed. Under the right conditions, computer simulations suggest that the impactor's dense metallic core could have been lodged in the Moon's upper mantle, where it would remain to this day, billions of years after the collision. The second hypothesis suggests the mass might be a concentration of dense oxides left over from the final stages of the lunar magma ocean's solidification. Based on the coincidence of such a large mass anomaly sitting precisely within the solar system's largest known impact structure, most researchers currently lean toward the impactor core explanation, though resolving the question with certainty will likely require future missions to the basin. The South Pole Aitken Basin has been a prime target for exploration. China's Chang'e 4 mission made history on January 3, 2019, when it became the first spacecraft ever to land on the far side of the Moon, touching down within the von Karman crater inside the basin. The mission deployed a small rover called U-22, which has studied the local soil and rock composition, finding materials that may have been excavated from deep within the lunar crust, or even the upper mantle by the original basin-forming impact. The Chang'e 6 sample return from within the basin in 2024 further advanced our understanding. Future missions to the south. Pole Aitken Basin, including possible sample return missions targeting different locations within the structure, are high priorities for the international scientific community. Samples from the basin could help resolve some of the most fundamental questions in lunar science, including the precise timing of the earliest bombardment and the composition of the deep lunar interior. Moving from the far side to the near side, the Imbrium Basin demands our attention. Mare Imbrium, the Sea of Rains, is one of the most prominent features visible on the Moon. It's the large, roughly circular dark patch in the Moon's upper left quadrant as seen from the northern hemisphere, easily visible to the naked eye. The basin that contains this dark plane is approximately 1,145 kilometers in diameter, making it one of the largest impact structures on the near side. The impact that created it occurred approximately 3.85 billion years ago, placing it near the end of the period of heavy bombardment during the Imbrian epoch of lunar history. In fact, this impact was so significant that it defines the beginning of the Imbrian period in the lunar stratigraphic timeline. The impactor that formed Imbrium was enormous, estimated at roughly 250 kilometers in diameter. Some recent analyses have suggested it may have been even larger, perhaps a protoplanetary body. The collision released energy beyond any earthly comparison. The resulting explosion excavated millions of cubic kilometers of lunar crust and upper mantle, blasting ejecta across nearly the entire visible face of the Moon. The Imbrium ejecta blanket, known as the Fra Mauro Formation, extends for hundreds of kilometers beyond the basin rim. The Apollo 14 mission landed on this ejecta deposit in February 1971, approximately 500 kilometers south of the basin rim, specifically to collect samples of Imbrium ejecta for dating. The ages obtained from these samples, clustering around 3.85 billion years, provided one of the key anchor points for the lunar timescale. The rim of the Imbrium Basin is defined by several mountain ranges that are among the most spectacular features on the Moon. The Montes Apenninus, the lunar Apennine Mountains, form the southeastern rim and rise to heights exceeding 5 kilometers above the Mare surface. The Apollo 15 mission landed at the base of these mountains in July 1971 at the Hadley Apennine site, where astronauts David Scott and James Irwin explored the mountain foothills and discovered the famous Genesis rock, a piece of anorthosite dated to roughly 4.1 billion years old. That measured age may reflect a metamorphic event rather than the rock's original crystallization, meaning the anorthosite itself could be even older, potentially a relic of the Moon's ancient primordial crust that was uplifted and exposed by the Imbrium impact. The Montes Caucasus form the northeastern rim, and the Montes Carpatus define the southern boundary. Together, these mountain ranges form a broken ring of peaks that trace the outline of the ancient impact. The shock waves from the Imbrium impact were so powerful that they are believed to have caused disruption on the opposite side of the Moon, a region of chaotic, hilly terrain directly antipodal to the Imbrium Basin, known as the Van de Graaff Formation, may have been created when seismic waves from the impact converged on the far side. This phenomenon, called antipodal focusing, concentrates the energy of a massive impact at the point diametrically opposite on the globe, potentially fracturing the crust and disrupting existing surface features. Similar antipodal disruption has been proposed for other large basins on the Moon and on Mercury. After the Imbrium Basin formed, it sat empty for roughly 200 to 600 million years. Then, beginning around 3.3 to 3.5 billion years ago, basaltic lava from the lunar interior welled up through fractures in the basin floor and began to flood the depression. Layer upon layer of lava flows accumulated, eventually filling the basin to depths of several kilometers in places. This lava is what we see today as the dark, smooth surface of Mare Imbrium. Wrinkle ridges, sinuous rills, and scattered secondary craters dot its surface, telling stories of compression, lava tube collapse, and ongoing bombardment that continued even as the mare was forming. The Oriental Basin completes our survey of titanic structures. Located on the Moon's extreme western limb, right at the boundary between the near side and the far side, Oriental is special not because of its size, though it is impressive, but because it is the youngest of the major multi-ring basins. Formed approximately 3.8 billion years ago, it has experienced less degradation from subsequent impacts than the older basins. This relative youth means Oriental is the best preserved example of a multi-ring basin in the entire solar system. Studying Oriental is like studying a textbook diagram of basin formation brought to life in stone. The outermost ring of Orientale, the Cordillera Mountains, has a diameter of approximately 930 kilometers. Inside this outer ring lie the Outer Rook Mountains, forming an intermediate ring roughly 620 kilometers across. And then the Inner Rook Mountains, an inner ring about 480 kilometers in diameter. The innermost zone is a relatively flat region partially flooded by small patches of dark basalt. This concentric ring structure is the hallmark of a multi-ring basin, and Oriental displays it more clearly than any other basin on the Moon. The mechanism by which multiple rings form during a very large impact has been debated for decades. The leading theories involve either oscillatory collapse of the transient cavity or the interaction of the expanding excavation cavity with pre-existing structural boundaries in the lunar crust. The Grail gravity mission provided new constraints on this problem, showing that the subsurface structure of Oriental is consistent with models in which the rings formed during the gravitational collapse of the transient crater. Because Oriental sits on the Moon's limb, it can be partially observed from Earth under favorable conditions of libration, the slight rocking of the Moon that periodically tilts slightly different portions into our line of sight. When libration brings the western limb toward us, observers can glimpse the Cordillera Mountains as a bright arc along the Moon's edge, but the full glory of Orientale's multi-ring structure is only visible from orbit. Spacecraft images reveal a stunning bullseye pattern, concentric arcs of mountains radiating outward from the center. It is one of the most beautiful geological features in the solar system. Beyond these three titans, several other basins deserve mention. The Serenitatis Basin, which hosts Mare Serenitatis, the Sea of Serenity, is approximately 740 kilometers in diameter and roughly 3.87 billion years old. The Apollo 17 mission in December 1972 landed at its southeastern rim in the Taurus-Littrow Valley, where astronauts Harrison Schmitt and Eugene Cernan collected samples that proved crucial for dating both the Serenitatis impact and the younger Tycho crater event. The Nectaris Basin, home to Mare Nectaris, is about 860 kilometers across and defines the beginning of the Nectarian period in lunar stratigraphy. The Apollo 16 mission landed on its ejecta blanket. The Crisium Basin, visible as the circular dark spot on the Moon's eastern limb, is about 740 kilometers in diameter. The Soviet Luna 24 mission returned samples from Mare Crisium in 1976, providing the last lunar samples returned to Earth until China's Chang'e 5 mission in 2020. Each of these basins tells a chapter of the same story, a period in the Moon's early history when enormous impactors, some hundreds of kilometers across, struck with enough force to reshape entire hemispheres. The basins they created became the dominant topographic features of the lunar surface, and when volcanism later flooded them with lava, they became the dark Maria visible to the naked eye. Every time you look at the Moon and notice those dark patches, you are seeing the scars of the most violent events in lunar history, partially healed by volcanic activity but never erased. Now let's shift our gaze from those enormous basins to individual craters, the kind you can observe through a telescope or even a good pair of binoculars. Among the thousands of craters that dot the lunar surface, certain ones have become famous not just for their visual beauty, but for what they've taught us about impact, physics, lunar chronology, and the forces that have shaped this world. Let's spend some time with 3 of the most celebrated. Tycho is, to many lunar observers, the most visually dramatic crater on the Moon. Located in the southern highlands at approximately 43 degrees south latitude, it commands attention not so much because of its size, which at 85 kilometers in diameter is respectable but not extraordinary, but because of its spectacular ray system and its remarkably fresh appearance. Tycho looks like it was formed yesterday in geological terms, and compared to most lunar craters, it practically was. Radiometric dating of samples linked to its ejecta, collected at the Apollo 17 landing site more than 2,000 kilometers away, indicates that Tycho formed approximately 108 million years ago. In the context of a 4.5 billion-year-old moon, that is astonishingly recent. Dinosaurs still roamed the Earth when the impactor that created Tycho struck the Moon. Through a telescope, Tycho is magnificent. The crater rim is sharp and well-defined, showing almost no degradation from subsequent impacts. The inner walls display prominent terracing, the characteristic staircase-like slumping of material that occurs when a large crater's walls collapse inward during the modification phase of formation. The crater floor lies roughly 4.8 kilometers below the rim crest. Rising from the center of the floor is a spectacular central peak, a mountain thrust upward from depth by the rebound of rock compressed during the impact. Multispectral images from the Clementine spacecraft revealed that this central peak has a different mineral composition from the surrounding material, consistent with the theory that central peaks bring up rock from deep beneath the surface, offering a window into layers that would otherwise remain hidden. But Tycho's most famous feature is its ray system, When the impactor struck, it blasted enormous quantities of crushed and melted rock outward in all directions. This ejecta landed on the surrounding terrain as a bright layer of fresh material that has not yet been darkened by the slow processes of space weathering. The result is a system of bright streaks radiating outward from the crater like the spokes of a wheel, extending for well over 1,500 kilometers across the lunar surface. One prominent ray stretches all the way to the Apollo 17 landing site in the Taurus Littrow Valley, approximately 2,000 kilometers from the crater. During the full moon, when the sun illuminates the near side head-on and shadows disappear, Tycho's ray system becomes the most prominent feature on the entire lunar disk, visible easily to the naked eye, as bright white lines converging on a brilliant point in the southern highlands. The fact that Tycho's ejecta reached the Apollo 17 site is itself a scientific gift. When astronauts Harrison Schmitt and Eugene Cernan explored the Taurus Littrow Valley in December 1972, they encountered a distinctive deposit on the South Massif Mountain. This deposit, which formed a prominent landslide, contained material that radiometric dating revealed to be approximately 108 million years old, far younger than the surrounding terrain. Scientists concluded that the arrival of Tycho ejecta at this distant location had triggered the landslide, and the age of the landslide material therefore provided the age of the Tycho impact itself. This indirect dating technique, linking a distant deposit to a specific crater through the ray system, illustrates the detective work that lunar science often requires. The impactor that created Tycho was probably an asteroid roughly 8 to 10 kilometers in diameter. Research published in 2007 in the journal Nature suggested a possible link between Tycho and the breakup of the parent body of the Baptistina asteroid family, a collisional fragmentation event in the asteroid belt that may have sent debris into orbits intersecting the inner solar system. However, subsequent studies have cast doubt on this specific connection, and the identity of Tycho's impactor remains uncertain. If Tycho is the young showpiece of the lunar surface, then Copernicus is the grand middle-aged monarch. Located in eastern Oceanus Procellarum, at about 10 degrees north latitude, Copernicus measures approximately 93 kilometers in diameter and is roughly 800 million years old, based on radiometric dating of ejecta samples believed to have been collected by the Apollo 12 mission, which landed on one of Copernicus's distant rays about 350 kilometers from the crater. The lunar cartographer Thomas Gwyn Elger called Copernicus the monarch of the moon, a title it richly deserves. Copernicus is a textbook complex crater. Its circular rim, which shows a subtle hexagonal outline in some images, rises above the surrounding plains, and its inner walls descend in a series of at least 3 distinct terraces, formed by the collapse and slumping of material during the crater's formation. The terraces create a staircase effect, a stunning visual when observed through a telescope at the right angle of illumination. Arc-shaped landslides are visible on the inner walls, evidence of the enormous gravitational forces that shaped the crater in the minutes and hours after impact. The floor lies approximately 3.8 kilometers below the rim crest. Unlike many older craters, Copernicus's floor has never been flooded by lava, probably because it formed relatively recently, long after the period of major volcanism on the moon had ended. Rising from the center of the floor is a cluster of at least 3 mountainous central peaks, climbing as high as 1.2 kilometers above the surrounding floor. These peaks are separated by valleys and form a rough line along an east-west axis. Remote sensing data from the Moon Mineralogy Mapper instrument on India's Chandrayaan-1 mission confirmed the presence of olivine-rich rock in Copernicus's central peaks. Olivine is a mineral typically associated with the mantle or deep crust, and its presence in the central peaks suggests that the Copernicus impact was powerful enough to uplift material from considerable depth, perhaps from the boundary between the crust and the upper mantle. Scientists were so interested in sampling these peaks that Copernicus was seriously considered as a landing site for the canceled Apollo 18 or later missions. Copernicus also has a prominent ray system, though its rays are more diffuse and feathery in appearance compared to Tycho's sharp, linear streaks. The rays extend as far as 800 kilometers across the surrounding mare, overlying rays from the craters Aristarchus and Kepler. The fact that Copernicus's rays overlie those from other craters helps establish its relative youth. An extensive pattern of smaller secondary craters surrounds the main crater, forming sinuous chains in the ejecta blanket. Some of these secondary crater chains were depicted as early as 1680 in a map by Giovanni Cassini, one of the earliest detailed observations of such features. Copernicus plays a pivotal role in lunar stratigraphy. The beginning of the Copernican period, the youngest era in lunar geological history, is defined by Copernicus itself. All geological units covered by Copernicus's rays are, by definition, older than the crater. Any crater that still retains bright, visible rays is classified as Copernican in age, meaning it formed within the last 800 million years or so. This stratigraphic significance, combined with its visual grandeur, makes Copernicus one of the most important and most studied craters on the Moon. The naming of the crater has its own story. In 1651, the Italian Jesuit astronomer Giovanni Riccioli assigned it the name Copernicus, after Nicolaus Copernicus, the Polish astronomer who formulated the heliocentric model of the solar system. As a Jesuit, Riccioli was publicly obligated to oppose heliocentrism, and he reportedly justified the naming by saying he had flung Copernicus into the ocean of storms. But astronomical historian Ewan Whitaker has suggested that the prominence of the crater Riccioli, assigned to Copernicus, may indicate that the Jesuits secretly supported heliocentrism and was ensuring that the great astronomer would have a worthy monument on the Moon. Whether this interpretation is correct, Copernicus the crater has certainly guaranteed that Copernicus the astronomer will never be forgotten. Our third portrait is Aristarchus, the brightest crater on the entire lunar surface. Located in the northwestern region of Oceanus Procellarum at about 24 degrees north latitude, Aristarchus measures approximately 40 kilometers in diameter and is estimated to be roughly 450 million years old. It is named after Aristarchus of Samos, the ancient Greek astronomer who was among the first to propose that the Earth revolves around the Sun. What makes Aristarchus immediately striking is its extraordinary reflectivity. The crater is so bright that it can be seen as a prominent white spot, even with the naked eye, during a full moon. When the crater is on the unilluminated portion of the Moon, it is sometimes visible by Earthshine alone. The faint reflected light from Earth that illuminates the moon's dark side. This extreme brightness results from the freshness of the impact and the composition of the target rock and ejecta. The interior, walls and floor of Aristarchus reflect roughly twice as much light as the average lunar surface. Through a telescope, Aristarchus reveals considerable internal complexity. The inner walls display terracing and prominent banding, with alternating bright and dark layers visible on the steep slopes. These bands may represent different geological strata exposed by the impact, layers of mare basalt, alternating with highland or impact-generated materials that had accumulated in this region over billions of years. The central peak rises from the crater floor, and the ejecta blanket extends outward in a rough pattern. Aristarchus sits on the Aristarchus Plateau, a large rectangular elevated region that is itself one of the most geologically interesting areas on the moon. The plateau shows evidence of extensive volcanism, including sinuous rills, channels carved by flowing lava. The most famous of these is Schroeter's Valley, also known as Valles Schroeteri, a massive sinuous rill that begins near a feature informally called the Cobra Head, a volcanic vent, and meanders for over 160 kilometers across the plateau. Schroeter's Valley is the largest sinuous rill on the moon, reaching widths of up to 10 kilometers and depths of about 1 kilometer. Its presence indicates that this region experienced significant lava eruptions in the past, with rivers of molten basalt carving channels into the surface. The Aristarchus region has also been the source of more reported transient lunar phenomena, brief changes in appearance such as brightenings, color shifts, or hazy patches than any other location on the moon. While many of these reports are likely observational artifacts caused by atmospheric conditions on Earth, the concentration of reports at Aristarchus has led some scientists to speculate that minor outgassing events, the release of gas from the lunar interior through faults and fractures, might occasionally occur in this geologically active region. The evidence for ongoing outgassing remains inconclusive, but the possibility adds another layer of intrigue to an already fascinating part of the lunar landscape. Beyond these three stars of the lunar surface, many other craters merit attention. Plato, a large 101-kilometer crater on the northern shore of Mare Imbrium, is notable for its exceptionally flat, dark floor, which has been flooded by basaltic lava. Through a telescope, the floor appears almost featureless, a stark contrast to the rugged terrain of unflooded craters. Clavius, a 231-kilometer crater in the southern highlands, is one of the largest craters visible on the near side and displays a distinctive arc of progressively smaller craters across its floor, each subsequent crater perched on the rim of the one before it, looking almost like a pearl necklace. Theophilus, a 100-kilometer complex crater on the northwestern shore of Mare Nectaris, overlaps the older crater Cyrillus, providing a clear stratigraphic relationship that demonstrates relative age. Theophilus's sharper rim and central peak indicate it is younger than the more degraded Cyrillus beside it, and Petavius, a 177-kilometer crater near the moon's southeastern limb, features a prominent central peak complex and a dramatic fracture known as Rimae Petavius that runs from the central peak to the southwestern wall, evidence of the enormous stresses that cracked the crater floor as it cooled and settled after formation. Each of these craters and thousands of others across the lunar surface tells its own story. Together they compose a comprehensive record of bombardment spanning virtually the entire history of the solar system. A record that Earth has lost, but the Moon has preserved. When you look at the Moon, the most immediately obvious feature isn't any individual crater. It's the contrast between the bright, rugged highlands and the dark, smooth plains. Those dark regions are the lunar maria, and their existence is intimately connected to the story of impact craters. The maria are what happened after the Great Basins formed. They represent a second chapter in the Moon's geological narrative, a chapter written not in the language of destruction, but in the language of volcanic creation. The word maria is Latin for seas. Early astronomers, peering through primitive telescopes, thought these dark, smooth expanses might actually be bodies of water. The misconception was understandable. The maria are darker than the surrounding highlands. They are relatively smooth and flat, and they fill large circular depressions that could be mistaken for shorelines. Michael van Langren published the first known map of the Moon in 1645, using this aquatic nomenclature, and the names stuck. We still call these features seas: Mare Tranquillitatis, the Sea of Tranquility; Mare Serenitatis, the Sea of Serenity; Mare Imbrium, the Sea of Rains; Oceanus Procellarum, the Ocean of Storms. Beautiful names for landscapes utterly devoid of water. What the maria actually are is vast plains of solidified basaltic lava. Between roughly 3.8 and 3.2 billion years ago, during the Imbrian and Eratosthenian periods, the Moon experienced extensive volcanic activity. Hot, fluid, basaltic magma from deep in the lunar mantle rose through fractures in the crust and erupted onto the surface. Because lunar basalt was exceptionally fluid, far more so than most terrestrial lavas, it spread across enormous areas before solidifying. These eruptions were not like the cone-building volcanoes of Earth, where viscous lava piles up near the vent. Lunar eruptions were more like the flood basalt events recorded in Earth's geological history, such as the eruptions that created the Deccan Traps in India or the Columbia River basalt group in the Pacific Northwest of the United States. Immense volumes of lava poured across the surface in sheet-like flows, each one perhaps 10 to 20 meters thick, gradually building up to cumulative thicknesses of hundreds of meters to several kilometers. The maria cover approximately 16% of the lunar surface, yet they represent less than 1% of the total volume of the lunar crust. They are relatively thin veneers spread across enormous areas. Individual flows overlapped and merged, creating the smooth, dark plains we see today. The lava flooded the low-lying impact basins that had been excavated during the period of heavy bombardment, filling them like water fills a bathtub. Most of the major maria, including Imbrium, Serenitatis, Tranquillitatis, and Crisium, sit within the floors of ancient impact basins, but the largest expanse of mare basalt, Oceanus Procellarum, the Ocean of Storms, does not correspond to any single recognized impact basin. It stretches across roughly 2,590 kilometers of the near side, covering more area than any other single mare, and its origin appears to be related to a unique combination of thermal and compositional conditions in the crust and mantle beneath it, rather than to any single basin-forming impact. The chemical composition of mare basalts, as revealed by samples returned by the Apollo and Luna missions, and by remote sensing from orbit, is distinctive. Lunar basalts are iron-rich and contain varying concentrations of titanium, a useful diagnostic for classification. Scientists group mare basalts into three broad categories: high titanium basalts, low titanium basalts, and very low titanium basalts. The Apollo 11 and Apollo 17 missions collected high titanium basalts from Mare Tranquillitatis and the Taurus Littrow Valley, respectively. Apollo 12 and Apollo 15 returned low titanium samples. The variation in titanium content reflects differences in the mantle source regions from which the magmas were derived, and in the conditions under which partial melting occurred deep in the Moon's interior. A critical difference between lunar basalts and their terrestrial counterparts is the near-total absence of water. Lunar basalts are extraordinarily dry. This dryness affects the physical properties of the magma, particularly its viscosity. Water dissolved in magma acts as a flux, lowering the melting temperature and affecting how easily the lava flows. The extreme dryness of lunar magma, combined with its high iron content, made it exceptionally fluid, which explains why it spread so widely and so thinly across the surface. One of the most enduring puzzles in lunar science is the dramatic asymmetry in the distribution of Maria between the Moon's near side and far side. Approximately 31% of the near side surface area is covered by mare basalts, while only about 2.5% of the far side is covered. This near-far asymmetry is striking. When spacecraft first photographed the far side, beginning with the Soviet Luna 3 in 1959, scientists were startled to find a landscape dominated almost entirely by bright, cratered highlands with only a few small, isolated patches of dark basalt. Several factors contribute to this asymmetry, and the full explanation remains an active area of research. The most important factor appears to be the distribution of heat-producing radioactive elements in the lunar interior. Data from the Lunar Prospector mission revealed that a large proportion of the Moon's inventory of potassium, rare earth elements, and phosphorus, collectively abbreviated as CREEP, is concentrated in the regions of Oceanus Procellarum and the Imbrium Basin on the near side. This concentration of radioactive heat-producing elements is now referred to as the Procellarum creep terrain. The enhanced heat production within this terrain kept the underlying mantle warmer for a longer period of time, promoting more extensive and more prolonged partial melting, and consequently, more volcanic activity at the surface. The mechanism by which creep became concentrated on the near side is debated. During the crystallization of the lunar magma ocean, the incompatible elements that make up creep, those elements that don't fit easily into the crystal structures of the minerals forming from the cooling magma, were progressively concentrated in the remaining liquid. Eventually, this creep-enriched residual liquid, the last fraction of the magma ocean to solidify, should have formed a global layer, sandwiched between the crust above and the crystallized mantle below. Something then caused this material to become concentrated on the near side, rather than remaining uniformly distributed. One hypothesis invokes the South Pole Aitken Basin impact itself. A 2022 study published in Nature Geoscience proposed that the enormous impact that created the South Pole Aitken Basin on the far side may have triggered a mantle overturn event that swept creep-rich material toward the near side, concentrating it in the region that would become the Procellarum creep terrain. Another contributing factor to the near-far asymmetry is the difference in crustal thickness. The far side crust is generally thicker than the near side crust, averaging roughly 60 kilometers on the near side compared to about 100 kilometers on the far side. Thicker crust makes it harder for magma to reach the surface because it must travel a longer path through solid rock. This crustal thickness difference may itself be related to the creep concentration and the thermal history of the two hemispheres. Interestingly, results from China's Chang'e 6 mission in 2024 revealed that mare volcanism on the far side persisted longer than previously thought. Analysis of basalt samples returned from the Apollo Basin within the South Pole Aitken structure yielded a radiometric age of approximately 2.8 billion years. This is younger than many near-side mare basalts and demonstrates that volcanic activity on the far side continued for over 1.4 billion years, even in the absence of the creep-rich heat sources that powered near-side volcanism. The magma source for these far-side basalts was apparently depleted in heat-producing elements, suggesting that other mechanisms, perhaps residual heat from the basin-forming impact itself, or tidal heating, or the insulating effect of the thick far-side crust, contributed to sustaining volcanism. The surfaces of the Maria are not featureless, despite their smooth appearance at a distance. Closer inspection reveals a variety of volcanic and tectonic features. Wrinkle ridges are low, sinuous ridges that meander across many mare surfaces. They formed when the weight of the accumulating lava caused the basin floor to sag and compress, buckling the surface into gentle folds. Sinuous rills are narrow, winding channels that were carved by flowing lava, similar to lava tubes or channels observed on Earth. Some rills may have been roofed lava tubes whose roofs later collapsed, creating the trenches we see today. Lava tubes that remain intact could potentially serve as shelters for future human habitation, offering protection from radiation, micrometeorite, to impacts, and the extreme temperature swings of the lunar surface. Dark halo craters are another interesting feature found in the Maria. These are impact craters that have excavated darker material from beneath a lighter surface layer, or lighter material from beneath a darker layer, creating a halo of contrasting brightness around the crater. They provide information about the subsurface stratigraphy, revealing what lies beneath the surface without the need for drilling. The radiometric ages of mare basalt samples span a range from about 4.2 billion years for the oldest to about 3.16 billion years for the youngest returned samples. Updated measurements from China's Chang'e 5 mission, which returned samples from a young volcanic province in northern Oceanus Procellarum in December 2020, revealed basalts as young as 2.03 billion years, extending the known duration of lunar volcanism significantly. Crater counting ages suggest that some mare flows may be even younger, perhaps as young as 1.2 billion years, though these youngest ages are less certain because they lack the calibration provided by actual sample return. The history of the Maria is, in essence, the story of the Moon's internal heat engine. The radioactive elements that kept the mantle warm enough to produce magma have been gradually decaying over billions of years, reducing the heat supply. The Moon has been cooling, its internal fires dying. Volcanic activity slowed and eventually ceased entirely. The last lava flows, solidified more than 1 billion years ago, and the moon today is geologically quiescent. No volcanoes erupt, no lava flows reshape the surface. The Maria stand as monuments to a more active past, frozen in time, waiting for observers to read their stories. One of the most profound contributions that lunar craters have made to science is providing a method for dating surfaces throughout the solar system. Without craters, we would have no way to determine the ages of landscapes on distant worlds that we've never visited and from which we have no samples. The techniques developed to date the moon's surface have become the foundation of planetary chronology, and they rely on two complementary approaches: counting craters and analyzing the radioactive decay of elements in rock samples. Let's start with crater counting, the simpler and more widely applicable of the two methods. The logic is elegant. When a surface is fresh, whether newly formed by a lava flow, resurfaced by an impact, or created by any other geological process, it has no impact craters. From the moment it forms, it begins accumulating craters, as objects from space strike it at random intervals. The longer the surface has been exposed, the more craters it collects. Therefore, a surface with many craters is older than a surface with few craters. This seems straightforward, and in principle it is, but turning this simple logic into a precise dating tool requires considerable sophistication. Scientists don't just count the total number of craters in a given area. They measure the size-frequency distribution, the number of craters of each size per unit area. Small craters are far more common than large ones because small impactors are much more numerous than large ones. The size-frequency distribution follows a well-defined mathematical relationship, often described by a power law. By measuring this distribution for a given surface and comparing it to a reference distribution, scientists can determine the relative age of that surface. Crater counting can reliably tell you which surface is older or younger than another on the same world. A heavily cratered region on Mars, for example, is clearly older than a smooth, lightly cratered region nearby. But crater counting alone gives only relative ages, not absolute ages. It tells you that surface A is older than surface B, but it doesn't tell you that surface A is 3.5 billion years old. To convert relative ages into absolute ages, you need calibration points, places where you know both the crater density and the actual age of the surface in years. This is where the Apollo and Luna missions made their most enduring contribution to planetary science. Between 1969 and 1976, 6 Apollo missions and 3 Soviet Luna missions returned a total of approximately 382 kilograms of lunar samples to Earth. These samples came from specific locations on the moon's surface, locations whose crater densities could be precisely measured from orbital photographs. By dating the samples using radiometric techniques and measuring the crater densities at the corresponding landing sites, scientists created a calibration curve linking crater density to absolute age. This curve is the cornerstone of the lunar chronology system. It transforms crater counting from a relative dating tool into an absolute one. Radiometric dating, the technique used to determine the absolute ages of the Apollo and Luna samples, exploits the decay of naturally occurring radioactive isotopes. Certain isotopes of elements like uranium, potassium, rubidium, samarium, and argon are unstable. Over time, they decay into different elements, called daughter products, at rates that are precisely known and unaffected by temperature, pressure, or chemical environment. By measuring the ratio of parent isotopes to daughter products in a rock sample, scientists can calculate how long the decay process has been occurring, and hence how long ago the rock solidified from a molten state. Several different radioactive decay systems are used for lunar samples. The potassium-argon system, which measures the decay of potassium-40 to argon-40, is useful for dating samples, ranging from a few 100 million to several billion years old. The rubidium-strontium system tracks the decay of rubidium-87 to strontium-87. The uranium-lead system, which is among the most precise, exploits the decay of uranium-238 to lead-206 and uranium-235 to lead-207. The samarium-neodymium system is particularly useful for dating very ancient rocks. By applying multiple dating techniques to the same sample and checking for consistency, scientists can achieve remarkable precision, often determining ages to within a few tens of millions of years for rocks that are billions of years old. The Apollo landing sites were not chosen at random. They were selected to sample a range of different geological units, from ancient highlands to younger mare basalts, providing calibration points spanning a broad range of ages. Apollo 11 landed on Mare Tranquillitatis, returning basalt samples dated to approximately 3.6 to 3.8 billion years. Apollo 12 landed in Oceanus Procellarum on younger basalts, approximately 3.15 to 3.35 billion years old. Apollo 14 collected Fra-Mauro Formation ejecta from the Imbrium impact, dated to approximately 3.85 billion years. Apollo 15 explored the Hadley Apennine region at the rim of the Imbrium Basin, collecting both mare basalts and highland materials. Apollo 16 landed in the Descartes Highlands, the only mission to a purely highland site, recovering some of the oldest lunar samples, including orthosites with ages broadly ranging from 4.3 to 4.5 billion years, depending on the sample and dating method. And Apollo 17 landed in the Taurus Littrow Valley at the edge of Mare Serenitatis, collecting both ancient highland rocks and relatively young volcanic glass beads. The Soviet Luna missions added valuable data points. Luna 16 returned samples from Mare Fecunditatis in September 1970, the first automated lunar sample return. Luna 20 collected highland samples from the Apollonius Highlands in February 1972. And Luna 24 returned core samples from Mare Crisium in August 1976, the last lunar sample return mission until China's Chang'e 5 in December 2020. Together, these missions provided approximately a dozen calibration points for the lunar chronology curve. The curve shows a steeply declining impact rate in the Moon's early history, followed by a more gradual decline over the past 3 billion years. The specific shape of this curve, whether it declines smoothly or shows a spike corresponding to the late heavy bombardment, remains a subject of ongoing research, as we discussed earlier. But the overall trend is clear. The rate of cratering was much higher in the past than it is today. The lunar chronology curve is then extrapolated to other bodies in the solar system. To estimate the age of a surface on Mars, for example, scientists first measure the crater size frequency distribution on the Martian surface they're interested in. They then convert the Martian crater density to an equivalent lunar crater density by accounting for differences in the impact environment between the two worlds. Mars is closer to the asteroid belt than the Moon, so it receives more impacts per unit area per unit time by a factor of roughly 2 to 5, depending on the model used. Mars also has a different surface, gravity, which affects crater size, and an atmosphere, which can prevent the smallest impactors from reaching the surface. After making these corrections, the Martian crater density is compared to the lunar chronology curve to obtain an age estimate. This extrapolation introduces significant uncertainties. The correction factors for different impactor populations, different surface gravities, different atmospheric conditions, and different target materials are all imperfectly known. For Mars, the uncertainty in absolute ages derived from crater counting can exceed 2 billion years in the worst cases, particularly for very old or very young surfaces. For Mercury, which is closer to the Sun and experiences a different impactor population, the uncertainties are similarly large. Despite these limitations, crater counting remains the only method available for dating surfaces on bodies from which we have no returned samples. It has been applied to Mercury, Venus, Mars, the moons of Jupiter, and Saturn, and even to asteroids visited by spacecraft. Recent advances have improved the method significantly. High-resolution imagery from missions like the Lunar Reconnaissance Orbiter, Mars Reconnaissance Orbiter, and Messenger at Mercury has allowed scientists to count smaller craters and identify secondary craters more reliably. Secondary craters, those formed by debris ejected from a primary impact, can contaminate crater counts and lead to spuriously old age estimates if they are mistakenly counted as primary impacts. The ability to recognize and exclude secondaries is crucial for accurate dating. Computer algorithms using machine learning and neural network architectures have also been developed to automate crater detection and counting. These crater detection algorithms can process vast amounts of imagery far more quickly than human observers, generating global crater catalogs containing hundreds of thousands of craters. While automated methods still require human oversight to verify accuracy, they have dramatically increased the efficiency and consistency of crater counting studies. The ongoing debate over the lunar chronology highlights an important point. Our understanding of the chronological framework continues to evolve. New sample return missions, like China's Chang'e 5 and Chang'e 6, are adding new calibration points to the curve. The Chang'e 5 basalts, dated at approximately 2.03 billion years, filled a significant gap in the calibration curve between the youngest Apollo samples at about 3.1 billion years and the present day. Future missions targeting the far side, the polar regions, or specific geological units of known crater density will continue to refine the chronology. Each new data point narrows the uncertainties and brings us closer to a precise, absolute timeline for the Moon's history, and by extension, for the entire inner solar system. There is one more dating technique worth mentioning, although it applies specifically to the Moon. Cosmic ray. Exposure dating measures how long a rock has been sitting on the lunar surface, exposed to the constant bombardment of cosmic rays from space. When high-energy cosmic ray particles strike the surface of a rock, they generate distinctive isotopes through nuclear reactions. By measuring the concentrations of these cosmogenic isotopes, scientists can determine how long the rock has been at or near the surface. This technique is particularly useful for determining when a particular impact event excavated material and brought it to the surface. It's a complementary tool to radiometric dating, providing different but related information about the history of the sample. Together, these dating methods have allowed scientists to construct a remarkably detailed timeline for the Moon. We know when the crust solidified, when the major basins formed, when the maria were flooded with lava, when specific craters were excavated, and how the rate of bombardment has changed over time. This timeline, anchored by returned samples and extended by crater counting, is one of the most valuable scientific products of the space age. And it all began with a simple act of counting circles on a photograph. One of the most surprising discoveries about the Moon in recent decades has nothing to do with ancient impacts or volcanic eruptions. It has to do with water, specifically water ice, hiding in some of the coldest, darkest places in the entire solar system. Places that exist because of the very craters we've been exploring. For most of the history of lunar science, the Moon was considered utterly dry. Apollo astronauts brought back 382 kilograms of rock, and careful chemical analysis revealed no detectable water. Scientists concluded that the Moon was one of the driest objects in the solar system. The extreme conditions of its formation, born from a collision violent enough to vaporize rock, would have driven off any volatile compounds, including water. The Moon has no atmosphere to speak of, no weather, no rain. Surface temperatures on the sunlit side can exceed 120 degrees Celsius, easily hot enough to vaporize any exposed ice almost instantaneously. The idea that water might exist on the Moon seemed absurd, but in 1961, even before the first Apollo landing, theoretical physicist Kenneth Watson published a paper proposing a mechanism by which water could persist on the Moon despite these hostile conditions. Watson pointed out something remarkable about the Moon's geometry. Because the Moon's rotation axis is tilted only 1.54 degrees relative to the plane of its orbit around the Sun, sunlight strikes the polar regions at extremely shallow angles. Deep craters near the poles have floors that never receive direct sunlight ever. The Sun simply never rises high enough to peek over the crater rim. These regions, known as permanently shadowed regions, exist in perpetual darkness. Without sunlight, the temperatures in these permanently shadowed regions plummet to extraordinary lows. Measurements by the Diviner Lunar Radiometer instrument on the Lunar Reconnaissance Orbiter have recorded temperatures as low as 25 to 35 Kelvin, which is roughly minus 248 to minus 238 degrees Celsius, or minus 415 to minus 397 degrees Fahrenheit, in some permanently shadowed craters near the South Pole. These are among the coldest naturally occurring temperatures measured anywhere in the solar system, colder even than the surface of Pluto. At these temperatures, water ice is thermodynamically stable. If water molecules from any source, a comet impact, outgassing from the lunar interior, or delivery by the solar wind, happen to migrate into one of these cold traps, they will freeze and remain frozen essentially forever. The ice accumulates over billions of years, molecule by molecule, creating deposits that could potentially be quite substantial. The first real evidence for lunar polar ice came in 1994, when NASA's Clementine mission detected enhanced radar reflections from craters near the South Pole, suggestive of ice deposits. This was intriguing but inconclusive, as rough rocky terrain can also produce enhanced radar returns. 4 years later, the Lunar Prospector mission used a neutron spectrometer to map hydrogen concentrations across the lunar surface. Neutrons produced by cosmic ray interactions with the lunar soil are slowed down when they encounter hydrogen atoms, which have a similar mass. The Lunar Prospector data showed clear enhancements in hydrogen concentration near both poles, exactly where permanently shadowed regions are concentrated. This was strong indirect evidence for water ice. But the definitive proof came on October 9, 2009, when NASA's Lunar Crater Observation and Sensing Satellite, known as LCROSS, deliberately slammed a spent Centaur rocket stage into Cabeus Crater, a permanently shadowed crater near the South Pole. The empty rocket shell, weighing about 2,300 kilograms, hit the crater floor at approximately 2.5 kilometers per second, creating a plume of debris that rose above the crater rim and into the sunlight, where it could be analyzed by the shepherding LCROSS spacecraft trailing behind. The results were unambiguous. Spectroscopic analysis of the impact plume detected water vapor and ice grains. Approximately 155 kilograms of water vapor and water ice were ejected into the LCROSS field of view. Based on the amount of soil excavated by the impact and the amount of water detected, scientists estimated the water ice concentration in the upper layers of Cabeus Crater to be roughly 5.6% by weight, with an uncertainty of about 2.9%. That might sound modest, but it was a landmark confirmation. The permanently shadowed regions of the Moon do indeed contain water ice. The LCROSS impact also detected a surprising variety of other volatile compounds in the plume. In addition to water, instruments registered the signatures of carbon monoxide, carbon dioxide, hydrogen sulfide, methane, ammonia, and several other compounds. Some of these, like mercury and silver, were unexpected. The diversity of volatiles suggested that the cold trap in Cabeus had been collecting material from multiple sources over a very long period of time. Cometary impacts delivering water and organic compounds, solar-wind interactions, generating hydrogen, volcanic outgassing, contributing carbon-bearing gases, and micrometeorite impacts delivering trace metals. Since LCROSS, additional evidence for lunar polar ice has continued to accumulate. In 2018, a study published in the Proceedings of the National Academy of Sciences, led by Shuai Li and colleagues, provided the first direct and definitive identification of water ice on the Moon's surface using data from the Moon Mineralogy Mapper instrument on India's Chandrayaan-1 orbiter. The instrument detected absorption features at near-infrared wavelengths that are uniquely characteristic of water ice, as opposed to hydroxyl or bound water in minerals. The detections were concentrated within permanently shadowed regions at both the North and South Poles, with more than 90% of the confirmed ice detections located within 10 degrees of the poles. A 2024 study by Timothy McClanahan of NASA's Goddard Space Flight Center, published in the Planetary Science Journal, found that water ice deposits are widespread within permanently shadowed regions at latitudes as low as 77 degrees south, extending well beyond the immediate vicinity of the South Pole. The study mapped where ice is likely and less likely to be found, identifying that the greatest ice concentrations occur near the coldest locations within permanently shadowed regions, those below 75 Kelvin, and near the base of poleward-facing slopes within those regions. For each surface square meter overlying these deposits, the study estimated at least 5 additional liters of ice within the top meter of regolith compared to surrounding areas. More recent research from 2023, published in Science Advances, added an important temporal dimension. The study found that most of the Moon's permanently shadowed regions are relatively young in geological terms, arising less than 2.2 billion years ago as the Moon's obliquity gradually decreased. This has significant implications because most major sources of lunar water, including cometary impacts and volcanic outgassing, peaked much earlier in the Moon's history, more than 3.5 billion years ago. This mismatch between the age of the cold traps and the timing of the major water delivery events means that the amount of ice preserved in these regions may be considerably less than older estimates suggested. The ice that does exist likely accumulated from more modest, ongoing sources like the solar wind and the relatively rare cometary impacts of the last 2 billion years. The practical importance of lunar polar ice cannot be overstated. Water is one of the most valuable resources imaginable for future lunar exploration. It can be split into hydrogen and oxygen through electrolysis, providing breathable oxygen for habitats and hydrogen fuel for rockets. Using locally sourced water instead of launching it from Earth would reduce mission costs dramatically, since every kilogram launched from Earth's surface to the Moon costs thousands of dollars. If the permanently shadowed regions contain sufficient quantities of accessible ice, they could become the strategic focal points of a sustained human presence on the Moon. This is one of the primary reasons NASA's Artemis program has targeted the lunar South Pole for its planned landing sites. The proximity of permanently shadowed ice deposits to regions of near-permanent sunlight on elevated terrain nearby, which could provide solar power, makes the South Polar region an ideal location for a long-duration outpost. However, as recent assessments from scientists have emphasized, significant uncertainties remain. The L-cross measurement was a single-point experiment at a single location. We still lack comprehensive high-resolution maps of ice distribution, concentration, and depth across the full range of permanently shadowed regions. As lunar scientist Norbert Schorghofer has noted, the field of lunar polar volatiles is still in its early stages, and definitive reproducible evidence of the ice's abundance and accessibility has yet to be established. South Korea's KPLO orbiter, carrying NASA's ShadowCam instrument, is beginning to peer into the dark, permanently shadowed regions with higher resolution than ever before, and future surface missions, including possible rover missions designed to drill into the ice deposits, will be essential for answering these critical questions. The craters that create these cold traps are, in a sense, doing double duty. They record the history of bombardment, as all craters do, but they also serve as natural freezers, preserving volatile compounds that would otherwise be lost to space. The very impacts that scarred the Moon's polar regions also created the conditions for those scars to become treasure vaults, repositories of water and other materials delivered over billions of years by comets, asteroids, and the solar wind. It is a remarkable twist in the story of lunar craters. instruments of destruction that became vessels of preservation. We have spent most of our journey focused on the moon itself, but one of the most powerful aspects of studying lunar craters is what they teach us about every other solid body in the solar system. The moon is the Rosetta Stone of planetary science, a translation key that allows us to read the geological histories of worlds we've barely explored. And impact craters are the common language, the universal script found on every rocky and icy surface from Mercury to the moons of Neptune and beyond. The concept is elegant in its simplicity. Every solid body in the solar system has been bombarded by impactors throughout its history. Every solid body, therefore, has craters. By understanding how craters form on the moon, where we have the best combination of detailed imagery, returned samples, and a well-calibrated chronology, we can interpret the craters we observe on other worlds. The moon serves as the calibration standard, the reference against which all other cratered surfaces are compared. Consider Mercury, the innermost planet. NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, and the ongoing Bepi-Colombo mission, a joint venture of the European Space Agency and the Japan Aerospace Exploration Agency, have mapped Mercury's surface in detail. What they found was a world that, at first glance, looks remarkably like the moon. The surface is heavily cratered. Large impact basins are scattered across the globe. Smooth plains, analogous to the lunar Maria, fill many of the largest basins. The Caloris Basin, Mercury's largest recognized impact structure at approximately 1,550 kilometers in diameter, bears a strong resemblance to the moon's Imbrium Basin. Both are enormous multi-ring structures that were later partially flooded by volcanic lavas. But closer inspection reveals important differences. Mercury's craters tend to have proportionally smaller ejecta blankets than lunar craters of the same size. This is because Mercury's surface gravity is about 2.4 times the moon's, so ejected material doesn't travel as far before falling back to the surface. Mercury also has unique features called hollows, bright, irregularly shaped depressions found on crater floors and central peaks that have no direct analog on the moon. Hollows appear to form through the sublimation or thermal decomposition of volatile, rich material near the surface, a process driven by Mercury's extreme proximity to the Sun and the intense solar radiation that heats its surface. Mercury also displays a global system of thrust faults and wrinkle ridges, evidence that the planet contracted as its interior cooled, a process more pronounced on Mercury than on the moon due to Mercury's larger relative iron core. By comparing crater densities on Mercury to the lunar chronology curve, adjusted for the different impactor flux at Mercury's orbital distance, scientists have estimated ages for various Mercurian terrains. The heavily cratered highlands of Mercury appear to be roughly contemporaneous with the lunar highlands, suggesting both worlds experienced intense bombardment during the same period. The smooth volcanic plains filling the Caloris Basin and other areas appear to date from roughly 3.5 to 3.8 billion years ago, similar in timing to the lunar Maria, though the exact ages carry substantial uncertainties because the impactor population at Mercury is imperfectly known. Mars tells a different and more dramatic story. Mars has an atmosphere, weather, flowing water in its past, and active erosion and deposition that modify and sometimes erase craters. Over time, studying Martian craters requires accounting for processes that don't exist on the airless moon. Wind erosion can partially fill craters with sand and dust. Water erosion in Mars is wetter, past carved channels that cut through crater walls, and deposited sediments on crater floors. Some of the most striking features on Mars are crater lakes, impact craters that once held standing bodies of water, evidenced by inlet and outlet channels, delta deposits, and layered sedimentary rocks on their floors. Gale Crater, a 154-kilometer impact structure where NASA's Curiosity rover has been operating since August 2012, is perhaps the most famous example. The crater contains Mount Sharp, a 5-kilometer-high mound of layered sedimentary rock that records hundreds of millions of years of environmental change. Curiosity had been climbing Mount Sharp, analyzing each layer of rock to understand how the environment evolved from warm, wet conditions that could have supported microbial life to the cold, dry conditions of today. The crater itself, formed roughly 3.5 to 3.8 billion years ago, provided the basin that collected water, sediments, and potentially the ingredients for life. Without the impact that created the crater, none of this geological and potentially biological history would have been preserved. Jezero Crater, where NASA's Perseverance rover landed in February 2021, is another crater lake with a clearly preserved river delta. The 49-kilometer crater was deliberately selected as a landing site because the delta deposits are considered among the most promising places on Mars to search for biosignatures, traces of ancient life preserved in the rock record. Perseverance has been collecting samples from the delta and crater floor, samples that are intended to be returned to Earth by a future Mars sample return mission. If those samples contain evidence of past life on Mars, it will be an impact crater that preserved the evidence. The Martian dichotomy, the stark difference between the heavily cratered southern highlands and the smooth northern lowlands, is itself one of the great mysteries of Mars. One leading hypothesis proposes that the northern lowlands were created by an enormous impact early in Mars's history, a collision that would have excavated a basin covering roughly 40% of the planet's surface. If this interpretation is correct, the hypothetical Borealis Basin would be by far the largest impact structure in the solar system, dwarfing even the Moon's South Pole Aitken Basin. The evidence remains actively debated. The circular outline of the lowland boundary, the thin crust beneath the lowlands, and the presence of buried structures consistent with a basin rim all support the impact hypothesis, but alternative explanations involving mantle convection and endogenic processes remain equally viable, and the question is far from settled. Beyond the terrestrial planets, impact craters are found on virtually every solid body that has been imaged in sufficient detail. The icy moons of Jupiter and Saturn display craters in ice rather than rock, and the behavior of ice under impact conditions differs from rock in interesting ways. Ice is weaker than rock, so craters in ice tend to be shallower relative to their diameter. On bodies with subsurface liquid water oceans, like Jupiter's moon Europa, the ice shell is continuously being resurfaced by geological activity, erasing older craters and leaving only the most recent ones visible. The paucity of craters on Europa's surface is actually one of the strongest arguments for an active geology and a young surface, possibly only tens of millions of years old. Saturn's moon Mimas is visually dominated by Herschel crater, a 139-kilometer-wide impact structure that covers roughly one-third of the moon's 396-kilometer diameter. The impact that created Herschel nearly shattered Mimas entirely. Fractures on the opposite side of the moon are thought to be caused by seismic waves from the impact converging at the antipodal point, the same mechanism we discussed for the Imbrium Basin's antipodal effects on the moon. Even small bodies bear the marks of impacts. The asteroid Vesta, visited by NASA's Dawn spacecraft from 2011 to 2012, has an enormous impact basin called Rhea Silvia at its south pole, roughly 505 kilometers in diameter on a body only 525 kilometers across. The impact that created Rhea Silvia excavated roughly 1% of Vesta's volume and sent fragments of the asteroid on trajectories that eventually delivered them to Earth as head meteorites, one of the largest known classes of meteorites. In every case, the same fundamental physics of hypervelocity impact applies. The shock waves, the excavation, the modification, the ejecta, the secondary cratering, these processes are universal. What changes from world to world are the details: surface gravity, target composition, atmospheric effects, surface temperature, and the presence or absence of volatiles all modify the outcome. But the basic process, an object moving at cosmic velocities striking a solid surface, is the same everywhere. Studying craters on one world illuminates craters on every other world. This universality is what makes the lunar crater record so scientifically valuable. The moon is the calibration standard, the baseline against which all other cratered surfaces are measured. Its airless, geologically inactive surface preserves a near-complete record of bombardment, extending back more than 4 billion years. Its proximity to Earth makes it accessible for sample return and detailed remote sensing, and its well-calibrated chronology, built painstakingly from Apollo and Luna samples, provides the only absolute anchor for the crater-based dating of every other solid body in the inner solar system. Without the moon, our understanding of the timing and intensity of bombardment throughout the solar system would be vastly poorer. Lunar craters are, quite literally, the key that unlocks the history of worlds. We've traced the story of lunar craters from the moon's violent birth to the present day. We've explored the physics of impact, the titanic basins, the famous craters, the volcanic Maria, the methods scientists use to read the lunar record, the ice hidden in polar shadows, and the way the moon illuminates the histories of other worlds. Now let's look forward, because the story of lunar craters isn't finished. A new chapter is about to begin. As of early 2026, humanity is preparing to return to the moon for the first time in over half a century. NASA's Artemis program, conceived as the successor to Apollo, aims not merely to revisit the moon, but to establish a sustained human presence there, one that will enable scientific exploration on a scale that the Apollo astronauts could only dream of. The Artemis II mission is currently targeting a launch no earlier than March 2026 from Kennedy Space Center in Florida. This mission will carry 4 astronauts, NASA's Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen, on a roughly 10-day free return trajectory around the moon and back to Earth aboard the Orion spacecraft, launched atop the Space Launch System rocket. No astronauts will land on the lunar surface during Artemis II. The mission is designed as a crewed test flight, verifying that the spacecraft, life support systems, and navigation systems perform correctly with humans on board in deep space. It will be the first crewed mission around the Moon since Apollo 17 in December 1972, more than 53 years ago. Glover will become the first person of color, Koch the first woman, and Hansen the first non-American to travel around the Moon. The mission took a significant step forward on February 2nd and 3rd, 2026, when NASA conducted a wet dress rehearsal, a pre-launch test that involved loading cryogenic propellant into the rocket's tanks and running through countdown procedures. The test encountered several challenges, including a liquid hydrogen leak and extended timelines for ground crew operations, which prompted NASA to postpone the launch from the original February window to March 2026. A second wet dress rehearsal will be needed before a launch date is confirmed. Despite these delays, the program is moving forward, and the site of the fully assembled rocket on Launch Pad 39B at Kennedy Space Center, illuminated by the full moon on the night of February 1st, 2026, was a powerful reminder that humans are finally heading back. Artemis III, currently expected to launch no earlier than mid-2027, is the mission that will return humans to the lunar surface. The plan calls for 4 astronauts to fly to the Moon aboard Orion, where 2 of them will transfer to a human landing system, a modified version of SpaceX's Starship, and descend to the surface near the lunar South Pole. This will be the first crewed lunar landing since 1972, and the first time any human has visited the Moon's South Polar region. The landing site selections, of which NASA has identified 9 candidate regions, are all near the South Pole, chosen specifically for their proximity to both permanently shadowed regions, where ice deposits may be accessible, and areas of near-permanent sunlight on elevated terrain, which could provide solar power. Among the scientific instruments planned for the mission is the Lunar Environment Monitoring Station, a compact autonomous seismometer suite that will listen for moonquakes and impacts, providing new data on the Moon's interior structure and ongoing bombardment rate. Beyond Artemis, other nations are pursuing their own lunar programs with ambitious goals directly related to the science of craters and impact history. China's lunar exploration program has been particularly productive. The Chang'e 4 mission, which landed inside the South Pole Aitken Basin in January 2019, was the first spacecraft to operate on the Moon's far side. Its DeVald rover, Yutu-2, has been studying the local soil and rock, finding materials possibly excavated from deep within the crust or upper mantle by the ancient basin-forming impact. The Chang'e 5 mission returned near-side samples in December 2020, revealing basalts as young as 2.03 billion years, and providing a crucial new calibration point for the lunar chronology. And the Chang'e 6 mission, which returned far-side samples from within the South Pole Aitken Basin in June 2024, has already provided the best direct constraint on the basin's age and revealed that far-side volcanism persisted surprisingly late. Future Chinese missions, including Chang'e 7 and Chang'e 8, are planned to explore the South Polar region, with Chang'e 7 expected to include an orbiter, lander, rover, and a small flying probe that could hop into permanently shadowed craters to directly sample ice deposits. India's Chandrayaan program continues to contribute valuable data. Chandrayaan-1, launched in 2008, carried the Moon Mineralogy Mapper instrument that provided critical evidence for surface-exposed water ice at the poles. Chandrayaan-3, which successfully landed near the South Pole in August 2023, deployed a small rover that confirmed the presence of sulfur and other elements in the South Polar soil, with implications for understanding the composition of the ancient crust in this region. These missions, and others being planned by Japan, South Korea, the European Space Agency, and multiple private companies, represent an unprecedented wave of lunar exploration. Each mission adds new pieces to the puzzle, refining our understanding of the moon's geology, chronology, and resource potential. And at the heart of this understanding, the connective tissue linking all of these investigations together, are craters. Craters provide the framework, the stratigraphic context, the dating methodology, and often the specific science targets that drive lunar exploration. Many fundamental questions remain open, questions that future missions may answer. And as we'll explore shortly, those missions are not hypothetical. They are happening now. Astronauts are preparing to return. Robots are being launched. And the craters of the moon are waiting, as they always have, to yield their secrets to anyone patient and curious enough to study them. But before we look to the future, let's deepen our exploration of the craters themselves. We've surveyed the titanic basins and introduced some famous craters. Now, let's return to those individual landmarks of the lunar surface and explore them with the detail they deserve, because each one has far more to reveal than a first glance can show. These are craters that astronomers have studied for centuries, craters that have shaped our understanding of impact processes, and craters that you yourself can observe on any clear night with nothing more than a small telescope or a good pair of binoculars. Each one has a distinct personality, a set of characteristics that makes it unique, and each one has something to teach us. We begin with the most visually dramatic crater on the moon, Tycho. If you look at the full moon on a clear night, your eye is almost immediately drawn to a bright spot in the southern highlands. That bright spot is Tycho. It sits at roughly 43 degrees south latitude, deep in the cratered highlands south of the ancient Nubian basin, and it dominates its surroundings in a way few other craters can match. Its diameter is approximately 85 kilometers, about 53 miles, and it plunges roughly 4 kilometers below its rim. But it isn't the size that makes Tycho unforgettable. It's the rays. Tycho possesses the most spectacular ray system of any crater on the moon's near side. Long, bright streaks of ejected material radiate outward from the crater in every direction, stretching for enormous distances across the lunar surface. Some of these rays extend over 1,500 kilometers from the crater's rim. One prominent ray reaches all the way to the Apollo 17 landing site in the Taurus Littrow Valley, more than 2,000 kilometers to the northeast. Astronauts Harrison Schmitt and Eugene Cernan, during the final Apollo mission in December 1972, collected samples from a landslide deposit that scientists believe was triggered by the arrival of Tycho's ejecta at that distant location. Those samples, when subjected to radiometric dating back on Earth, yielded an age of approximately 108 million years. If this connection is correct, and most researchers believe it is, then Tycho formed 108 million years ago, during the Cretaceous period on Earth, when dinosaurs still dominated the planet. An asteroid estimated at 8 to 10 kilometers in diameter slammed into the moon at that time, carving out Tycho in a matter of minutes. What makes Tycho's rays so bright is, paradoxically, its youth. On the moon, freshly excavated material is initially quite reflective, but over millions of years, exposure to the solar wind, to cosmic rays, and to the constant rain of micrometeorites gradually darkens the surface, a process scientists call space weathering. Because Tycho is only 108 million years old, an infant by lunar standards, its rays haven't had enough time to be fully darkened. They still gleam against the older weathered surface. Given enough time, perhaps another few 100 million years, those rays will fade until they're indistinguishable from the background terrain, just as the rays of older craters like Eratosthenes have already vanished. The interior of Tycho is as impressive as its exterior. The walls are sharply terraced, with multiple concentric ledges formed when enormous blocks of rock slumped inward during the crater's formation. The floor is covered in impact melt, rock that was heated to such extreme temperatures during the impact that it liquefied and flowed across the crater floor before solidifying. This impact melt shows a fascinating crisscrossing network of cracks and small hills, evidence of the complex cooling process the molten rock underwent. And rising from the center of the floor is a magnificent central peak, a mountain roughly 1,600 meters tall, formed from material that rebounded upward after being compressed by the initial shock of the impact. Lunar reconnaissance. Orbiter images have revealed an extraordinary detail on the summit of this central peak. A boulder approximately 120 meters wide, sitting in a notch near the top of the mountain, apparently flung there during the impact event itself. This single boulder is larger than a football field. It has been sitting on that mountaintop for 108 million years, undisturbed, because on the moon there is no wind, no rain, no earthquake to dislodge it. Tycho was one of the earliest craters drawn on lunar maps. In 1645, the Bohemian astronomer Antonius Maria Schirlaeus de Reta depicted its bright ray system on a map of the moon. The crater was later named after the great Danish astronomer Tycho Brahe by the Jesuit astronomer Giovanni Riccioli in his 1651 nomenclature system. Before Riccioli, the crater had been called by other names. Pierre Gassendi called it Umbilicus Lunaris, the navel of the moon. Michael van Langren labeled it after King Vladislav IV of Poland. Johannes Hevelius called it Mount Sinai, but it was Riccioli's name that stuck, and Tycho it has remained for nearly 4 centuries. The crater has captured the imagination of artists and writers as well. In Arthur C. Clarke's novel and Stanley Kubrick's film 2001, A Space Odyssey, a mysterious alien monolith is discovered buried beneath Tycho's surface. This fictional location was designated TMA-1, the Tycho Magnetic Anomaly. Clarke chose Tycho for a reason. Its youth, its dramatic appearance, and its prominence on the lunar surface made it the perfect location for a world-altering discovery. And while no alien monoliths have been found there, Tycho remains one of the highest priority targets for future exploration. A mission to Tycho could return samples that would directly date the impact, resolving any remaining ambiguity about when it formed. It would also provide access to material excavated from deep within the lunar crust, exposed in the crater walls and central peak, offering a window into the moon's interior that few other locations can match. From Tycho, let's travel northward to one of the most important craters in the history of lunar science, Copernicus. This magnificent crater sits slightly northwest of center on the moon's Earth-facing hemisphere, in the eastern reaches of Oceanus Procellarum, the Ocean of Storms. With a diameter of approximately 93 kilometers and a depth of about 3.8 kilometers, Copernicus is one of the most prominent craters visible from Earth. It can be spotted with binoculars and is easily visible through any small telescope. The 19th century lunar cartographer Thomas Gwynne Elgar gave it an enduring nickname, the Monarch of the Moon. The naming of Copernicus carries an ironic history. Giovanni Riccioli, the Jesuit astronomer who assigned names to most of the moon's major features in 1651, was publicly opposed to the heliocentric model of the solar system that Nicolaus Copernicus had championed. Riccioli claimed he flung Copernicus into the ocean of storms as a sign of his contempt for heliocentrism, but the plan backfired. The crater Riccioli chose turned out to be one of the finest on the moon, and astronomical historian Ewan Whitaker has speculated that Riccioli may have secretly supported the heliocentric model and deliberately gave Copernicus a magnificent crater to honor his legacy. Copernicus formed roughly 800 million years ago, possibly from debris related to the breakup of the parent body of asteroid 495 Eulalia. It is older than Tycho, but still young enough to retain visible ray patterns, though its rays are less prominent and less symmetrically arranged than Tycho's. The crater's rim has a discernible, hexagonal shape, a subtle geometric signature that likely reflects pre-existing fractures in the target rock that influenced the shape of the crater during formation. The inner walls display three distinct terrace levels, formed by the slumping and collapse of rock during the modification phase of the impact. These terraces are among the most well-defined on the moon. The floor of Copernicus has not been flooded by lava, unlike many of the older large craters. This is significant because it tells us that the volcanism that produced the Maria had largely ceased by the time Copernicus formed. The floor is rough and hummocky, covered in solidified impact, melt, and rubble. Near the center stand several peaks and groups of hills, remnants of the central uplift. These peaks rise to impressive heights, providing cross-sections of the crustal layers that were uplifted during the impact. In 1966, when spacecraft photography of the moon was still in its infancy, the American Lunar Orbiter 2 captured an oblique view of Copernicus that became one of the most celebrated images in the history of space exploration. The photograph showed the crater from an angle rather than directly overhead, revealing the dramatic topography of its walls, central peaks, and surrounding terrain in three-dimensional relief. It was widely published and became known simply as the picture of the century. Looking at that image, it is easy to see why Copernicus earned its royal title. The combination of terraced walls, rugged floor, prominent central peaks, and surrounding debris field creates a scene of imposing geological grandeur. Copernicus also serves as the naming reference for one of the three major periods of lunar history: the Copernican period, the most recent in the lunar timescale, is defined as the era in which craters retain visible ray systems. Any crater with intact rays is, by definition, Copernican in age. The period began roughly 1.1 billion years ago and continues to the present day. Every fresh, bright crater you see on the moon belongs to this era, and Copernicus is its archetype. Our third profile takes us to the brightest spot on the entire moon, Aristarchus. This crater, located in the northwestern quadrant of the near side, on the elevated Aristarchus Plateau within Oceanus Procellarum, has an albedo, a measure of reflectivity that is nearly double that of most other lunar features. It is so bright that it can be seen with the naked eye as a distinct point of light, and it is often visible even when illuminated only by earthshine, the faint reflected light from Earth that dimly illuminates the moon's dark hemisphere. The great astronomer William Herschel, observing in the late 1700s, once mistook Aristarchus for an erupting volcano because of its extraordinary brightness. Aristarchus is about 40 kilometers in diameter and sinks more than 3.5 kilometers deep, making it deeper than the Grand Canyon. It formed approximately 450 million years ago, placing it in the Copernican period, younger than Copernicus but older than Tycho. The crater is named after Aristarchus of Samos, the ancient Greek astronomer who first proposed a heliocentric model of the solar system, roughly 1,700 years before Copernicus revived and developed the idea. The extreme brightness of Aristarchus stems from two factors. First, its relative youth means space weathering has not yet significantly darkened the freshly exposed material. Second, and more intriguingly, the Aristarchus impact penetrated into material with an exceptionally high reflectance. The Hubble Space Telescope has detected high concentrations of the mineral ilmenite, a titanium oxide, in the crater. The central peak, which is the brightest feature, is composed of anorthosite, the ancient aluminium-rich rock that formed the moon's primordial crust. The impact excavated through billions of years of accumulated surface material and volcanic deposits to reach this ancient, bright bedrock, bringing it back to the surface. The geological setting of Aristarchus makes it one of the most scientifically fascinating locations on the moon. The Aristarchus Plateau itself is an elevated crystal block roughly 200 kilometers across, rising about 2 kilometers above the surrounding mare. This plateau is thought to be one of the most geologically diverse regions on the moon. It hosts not only the crater itself, but also the adjacent crater Herodotus, and, connecting the two, Valles Schrotteri, a sinuous rill carved by an ancient lava flow. Valles Schrotteri, also known as Schroeder's Valley, is the largest sinuous rill on the moon, beginning with a feature nicknamed the Cobra Head, a wide volcanic vent from which the lava once issued. The valley winds for over 160 kilometers across the plateau, a frozen record of volcanic activity that once transformed this landscape. Aristarchus is also the location most frequently associated with a controversial phenomenon known as transient lunar phenomena, brief, localized changes in brightness or color reported by observers over the centuries. Of all reported transient lunar phenomena across the moon's surface, Aristarchus accounts for a disproportionately large number. In 1971, when Apollo 15 passed 110 kilometers above the Aristarchus Plateau, Instruments detected a significant spike in alpha particle emissions, which are produced by the radioactive decay of radon-222 gas. The Lunar Prospector mission later confirmed radon emissions from this area. These observations suggest that gas is still seeping to the surface from the Moon's interior in this region, a tantalizing hint that the Moon is not entirely geologically dead. Whether these gas emissions are related to the historical reports of transient phenomena remains an open question, but the coincidence is suggestive. The Aristarchus Plateau was proposed as a potential landing site during the Apollo program. Had the program not been canceled after Apollo 17, a future mission might have explored this extraordinary region. It remains a high-priority target for future exploration. The combination of diverse rock types, volcanic features, potential ongoing geological activity, and the crater's unique composition make it a natural laboratory for understanding the Moon's history and internal processes. Beyond Tycho, Copernicus, and Aristarchus, the Moon is populated by dozens of other remarkable craters, each with its own story. Plateau, a large dark-floored crater in the northern highlands near the Alpine Valley, is notable for its extremely flat interior, suggesting it was flooded by lava after its formation. Theophilus, a younger crater that strikingly overlaps the older crater Cyrillus, near Mare Nectaris, provides a dramatic example of superposition, the principle that younger features overlie older ones. Kepler, a 32-kilometer crater in Oceanus Procellarum, has a bright ray system that, while less extensive than Tycho's, is still prominent at full moon. Stevinus, in the southeastern highlands, possesses asymmetric rays suggesting an oblique impact. And Giordano Bruno, a small but startlingly fresh crater on the far side, was once proposed to be only about 800 years old, based on a 1178 account by the English monk Gervase of Canterbury, who described what appeared to be a bright flash on the Moon's limb. However, most modern researchers are skeptical of this connection, noting that an impact creating a 22-kilometer crater would have produced a visible debris shower on Earth that was not recorded. The crater is more likely several million years old, its youthful appearance a result of its relatively recent formation on geological timescales. Each crater, whether famous or obscure, adds a data point to our understanding of the bombardment history of the inner solar system. Each preserves a record of the impactor's energy, the properties of the target's surface, and the processes that shaped the crater after it formed. Together they form a mosaic of evidence that scientists have been piecing together for decades and will continue piecing together for decades to come. When you look at the Moon, the feature that most readily catches the eye is the contrast between bright and dark regions. The bright areas are the ancient, heavily cratered highlands, composed primarily of anorthosite, a calcium-rich rock that crystallized from the lunar magma ocean over 4 billion years ago. The dark areas are the Maria, vast plains of solidified basaltic lava that filled many of the Moon's largest impact basins hundreds of millions of years after those basins formed. Understanding the Maria is essential to understanding lunar craters because the two are intimately connected. The basins provided the containers. The volcanism provided the fill. The Maria cover roughly 16% of the lunar surface, and they are overwhelmingly concentrated on the near side. When the Soviet probe Luna 3 returned the first Photographs of the Moon's far side. In 1959, scientists were startled to discover that the far side looks dramatically different from the near side. The dark maria that dominate the near side face are almost entirely absent on the far side. Only a few scattered patches of basalt exist there, mostly confined to the floors of very large craters. The vast majority of the far side is ancient, bright highland terrain, saturated with overlapping impact craters. This dramatic asymmetry between the two hemispheres has been one of the longest-standing puzzles in lunar science, and it has only recently begun to yield to explanation. The basaltic lavas that form the maria erupted from the Moon's interior between approximately 4.2 billion and 1.2 billion years ago, with the peak of volcanic activity occurring between roughly 3.8 and 3.2 billion years ago. These lavas were remarkably fluid, far more so than most terrestrial lavas. Their low viscosity allowed them to flow across enormous distances, sometimes traveling hundreds of kilometers from their source vents. Individual lava flows in Mare Imbrium have been traced for over 1,200 kilometers, and they achieved thicknesses ranging from roughly 10 to 40 meters per flow. Layer upon layer of these thin, extensive flows accumulated over hundreds of millions of years, gradually filling the basins to depths of several kilometers in places. The composition of the Mare basalts is distinctive. They are rich in iron and titanium compared to the highland rocks, which is why they appear so much darker. Using the classification scheme developed for terrestrial rocks, all Mare basalts are tholeiitic, a specific subtype of basalt, but lunar scientists have developed their own sub-classifications based on titanium content. High titanium basalts, with titanium dioxide concentrations reaching up to 15% by weight, are the darkest and are concentrated in certain areas, particularly in Mare Tranquillitatis, where the Apollo 11 mission landed. Low titanium basalts are lighter and more widespread. Very low titanium basalts represent the palest end of the spectrum. Remote sensing data from the Clementine mission showed that these categories are not discrete bins, but rather points along a continuum, with high titanium basalts being the least common overall. A special and scientifically important subgroup of lunar basalts is enriched in potassium, symbolized by K on the periodic table, rare earth elements, and phosphorus. This combination gives the group its acronym, CREEP. The CREEP signature is concentrated in a broad region of the near side, centered on Oceanus Procellarum and the Imbrium Basin, an area now referred to as the Procellarum Curepe terrain. This region contains a disproportionate share of the Moon's inventory of radioactive elements, specifically uranium, thorium, and potassium, whose decay generates internal heat. The enhanced concentration of heat-producing elements in the Procellarum Curepe terrain is strongly connected to the longevity and intensity of volcanism on the near side. The radioactive decay provided an internal heat source that kept the underlying mantle warm enough to produce magma for a longer time than elsewhere on the Moon. This is a key part of the explanation for why the maria are so much more abundant on the near side than on the far side. But CREEP alone doesn't fully explain the asymmetry. The crust of the Moon is significantly thicker on the far side than on the near side. Data from NASA's Grail mission, which mapped the Moon's gravitational field with unprecedented precision, confirmed this difference. The far side crust averages roughly 60 kilometers thick, while the near-side crust averages about 30 to 40 kilometers. For magma rising from the mantle, a thicker crust means a longer journey and a greater barrier to overcome. On the near side, with its thinner crust, magma could more readily reach the surface and erupt as lava flows. On the far side, much of the magma may have stalled within the crust, intruding into the rock without ever breaking through to the surface. This phenomenon of intrusive volcanism, magma that solidifies underground, has been increasingly recognized as a significant process on the far side. Recent results from China's Chang'e 6 mission, which returned samples from the Apollo Basin within the South Pole Aitken structure on the far side, have added remarkable new detail to this story. Analysis of basalt fragments from the Chang'e 6 samples revealed 2 distinct volcanic episodes on the far side, one at approximately 4.2 billion years ago from a creep-rich mantle source, and another, surprisingly young, eruption at 2.807 billion years ago from a creep-poor source. The younger age demonstrates that volcanic activity on the far side persisted for at least 1.4 billion years, even in the absence of significant radiogenic heating from creep elements. The depleted and refractory character of the far side mantle, combined with the thicker crust, helps explain why far side volcanism was so much less prolific than on the near side. But it did not cease entirely. These findings also confirmed that the crater counting chronology model developed for the near side is applicable to the far side as well, an important calibration for dating surfaces across the entire moon. The volcanic flooding of the basins created the familiar two-toned appearance of the moon that has inspired human imagination for millennia. Different cultures have seen different patterns in the arrangement of dark and light regions. European tradition speaks of the man in the moon. East Asian cultures see a rabbit pounding rice cakes. South American folklore imagines a grandmother's face. Hindu mythology describes the markings as the hands of a god. These varied interpretations all arise from the same physical phenomenon, the contrast between ancient, bright, heavily cratered highlands and younger, dark, smooth basaltic plains that filled the great impact basins during the moon's volcanic era. The relationship between craters and Maria plays out in other important ways as well. When lava flooded the basins, it submerged everything in its path. Craters that had formed on the basin floors before the lava arrived were partially or completely buried. Some of these ghost craters, as they are sometimes called, can be detected as faint circular ridges or discolorations on the mare surface, their outlines barely visible beneath the basalt veneer. Wrinkle ridges, low, sinuous ridges that wind across the Maria, are another product of the interaction between impact basins and volcanic infill. These ridges formed when the weight of the accumulated lava caused the underlying basin floor to subside, compressing the surface and forcing it to buckle upward along faults. Wrinkle ridges are among the most common small-scale features on the mare surfaces, and they record the mechanical response of the crust to the loading, imposed by millions of years of volcanic activity. One of the most important contributions of lunar craters to science has been their role as clocks. Because craters accumulate on any surface exposed to space, counting craters provides a means of estimating how old that surface is. An older surface has had more time to accumulate impacts, so it should have more craters per unit area than a younger surface. This principle, straightforward in concept but extraordinarily complex in practice, is the foundation of crater counting, one of the most powerful dating techniques in planetary science. The basic logic is simple. If you know how frequently impacts occur, and you count the number of craters on a surface, you can calculate how long that surface has been exposed. But the reality is far more nuanced. The rate of impact has not been constant over time. It was much higher in the early solar system and has declined dramatically since. The sizes of impactors follow a specific statistical distribution, with small impactors being far more common than large ones. And surfaces can be reset by geological processes. A lava flow that covers an older surface effectively resets the crater clock to zero because the new surface starts with no craters. Subsequent impacts on the lava flow then begin a new count. To convert crater counts into absolute ages, scientists need a calibration. This is where the Apollo samples become indispensable. The 6 Apollo missions and the 3 Soviet Luna sample return missions brought back a total of roughly 382 kilograms of lunar material from known locations on the surface. By dating these samples using radiometric techniques, primarily potassium-argon dating, rubidium-strontium dating, and uranium-lead dating, scientists determined the absolute ages of specific surfaces. They then counted craters on those same surfaces using high-resolution photographs. By matching crater densities to absolute ages at these calibration points, they constructed a mathematical relationship called the crater production function that allows them to estimate the age of any surface from its crater density alone. This calibration has been refined repeatedly over the decades. The original Apollo-era calibration was based on relatively few data points, and some of those points carried significant uncertainties. As new missions have returned additional samples, and as imaging technology has improved, the calibration has become more precise. The Chang'e 5 mission, which returned samples from Oceanus Procellarum in December 2020, provided a particularly valuable new calibration point at roughly 2 billion years, filling a gap in the previously sampled age range. And the Chang'e 6 samples from the far side have now extended the calibration to that hemisphere for the first time, confirming that the near-side-derived chronology is applicable globally. Crater counting has been used to date surfaces across the entire solar system. Once you have a calibrated crater production function for the Moon, you can, with appropriate adjustments for factors like gravity, impactor flux, and atmospheric shielding, apply similar reasoning to other bodies. Mars, Mercury, the moons of Jupiter and Saturn, even asteroids have been dated using crater counting techniques adapted from the lunar standard. The Moon serves as the Rosetta Stone of planetary chronology, the reference point against which all other surfaces in the inner solar system are measured. But the technique is not without limitations and controversies. One major challenge is the problem of secondary craters. When a large impactor strikes a surface, it ejects enormous volumes of material. Some of this ejecta falls back to the surface at high velocity, creating secondary craters that are morphologically similar to primary craters, but smaller and often clustered. If secondary craters are mistakenly counted as primary impacts, the resulting age estimate will be too old. Researchers have developed statistical methods to identify and exclude secondary crater populations, but the corrections are imperfect, and the issue remains a source of debate. Another challenge is the assumption of a known impactor flux. The crater production function is calibrated at the Moon, where we have ground truth ages from returned samples. Extending this function to other bodies requires assumptions about how the impactor flux varies with distance from the Sun, with proximity to the asteroid belt, and with the gravitational influence of nearby planets. These assumptions introduce uncertainties that grow larger the farther you move from the Moon. Despite these challenges, crater counting remains an invaluable tool. It is often the only means of dating surfaces on other worlds. Without the lunar calibration, our understanding of the chronology of the entire inner solar system would be far more limited. Every time a planetary scientist dates a surface on Mars or Mercury or an asteroid, they are relying, directly or indirectly, on work done at the Moon. The craters on the lunar surface are, in a very real sense, the calendar of the solar system. Among the most exciting recent developments in lunar science is the discovery that craters at the Moon's poles contain something remarkable: water ice. This discovery has transformed our understanding of the Moon and has profound implications for the future of human space exploration. The story begins with a peculiarity of the Moon's axial tilt. The Moon's rotation axis is inclined only 1.54 degrees relative to the ecliptic plane, the plane of its orbit around the Sun. This is an extremely small tilt, far less than Earth's 23.4 degree obliquity. The consequence of this minimal tilt is that the Sun never rises high above the horizon at the lunar poles. In the bottoms of deep craters near the poles, the Sun never rises at all. These regions, permanently shielded from direct sunlight, are called permanently shadowed regions. Within them, temperatures plunge to some of the coldest recorded anywhere in the solar system. NASA's Diviner Lunar Radiometer experiment, carried aboard the Lunar Reconnaissance Orbiter, has measured temperatures in some of these permanently shadowed craters as low as roughly 25 to 35 Kelvin, which is approximately minus 248 to minus 238 degrees Celsius, or minus 415 to minus 397 degrees Fahrenheit. These temperatures are colder than the surface of Pluto. At such extreme cold, water ice and other volatile compounds that land on the surface, delivered by comet impacts or produced by interactions between the solar wind and oxygen-bearing minerals, cannot evaporate. They are in effect trapped. These frigid craters act as cold traps, collecting and preserving volatile materials over billions of years. The first hints that water ice might lurk in these cold traps came in 1994, when the Clementine mission detected radar signatures in some south polar craters that were consistent with ice. In 1998, the Lunar Prospector Orbiter detected enhanced concentrations of hydrogen at both poles using its neutron spectrometer. Hydrogen is a key indicator of water because water molecules contain hydrogen atoms, and hydrogen signatures are relatively easy to detect from orbit. But these early measurements were ambiguous. The hydrogen could have been in forms other than water, such as solar wind protons embedded in the regolith, or hydrogen-bound in hydrated minerals. The definitive confirmation came on October 9, 2009, when NASA executed one of the most audacious experiments in the history of lunar exploration. The LCROSS mission, the Lunar Crater Observation and Sensing Satellite, deliberately crashed a spent Centaur rocket stage into Cabeus crater near the Moon's south pole. The Centaur struck the permanently shadowed floor of Cabeus at a speed of about 9,000 kilometers per hour, excavating a crater roughly 20 meters across and lofting approximately 350 metric tons of lunar material into space. 4 minutes later, the LCROSS shepherding spacecraft flew through the rising debris plume, its instruments analyzing the composition of the ejected material before it, too, struck the lunar surface. The results were extraordinary. The spectrometers aboard LCROSS detected clear signatures of water vapor and water ice in the plume. Analysis indicated that the plume contained approximately 155 kilograms of water, and that the concentration of water in the regolith at the impact site was roughly 5.6% by mass, with uncertainty of about 2.9%. In some portions of the plume, scientists detected what appeared to be near pure crystalline water ice, suggesting that in certain cold trap environments, ice can accumulate in relatively concentrated deposits rather than being thinly dispersed throughout the soil. But water wasn't the only discovery. The LCROSS plume contained a remarkably diverse cocktail of volatile compounds, including molecular hydrogen, carbon monoxide, hydrogen sulfide, ammonia, sulfur dioxide, methanol, mercury, and methane. The range of volatiles was strikingly similar to those found in comets from the outer solar system, supporting the idea that much of this material was delivered to the Moon by cometary impacts over billions of years, and then migrated to the polar cold traps, where it has been preserved ever since. Other sources are also possible. Solar wind protons interacting with oxygen-bearing minerals on the lunar surface can produce small amounts of water that gradually migrates to the poles. And in 2021, researchers demonstrated that the Earth wind, charged particles escaping from Earth's magnetosphere, can also interact with lunar surface minerals to generate water. In 2018, a comprehensive analysis of data from the Moon Mineralogy Mapper instrument aboard India's Chandrayaan-1 mission provided the first high-resolution map of confirmed water ice deposits on the lunar surface. The map showed ice present at both poles, concentrated in permanently shadowed craters, confirming the cold trap hypothesis at multiple locations simultaneously. Then, in 2020, NASA's Sophia Airborne Observatory, the Stratospheric Observatory for Infrared Astronomy, detected unambiguous spectral signatures of molecular water on sunlit portions of the lunar surface in the Clavius crater region. The concentrations were low, roughly equivalent to a 12-ounce bottle of water per cubic meter of soil. But the detection was significant because it demonstrated that water exists on the Moon even outside permanently shadowed regions. The water appears to be trapped within glasses or between grains of lunar soil, possibly produced by micrometeorite impacts that fuse soil grains with trace water. More recently, analysis of samples returned by China's Chang'e 5 mission identified a previously unknown mineral, designated ULM1, found in sunlit lunar soil. Water makes up more than 40% of this mineral sample by mass. While this discovery involves water chemically bound within a mineral crystal structure rather than free ice, it further expands our understanding of the diverse forms in which water can exist on the Moon. The discovery of lunar water ice has enormous practical implications. Water is heavy, and launching it from Earth to the Moon is prohibitively expensive, estimated at $2,000 to $20,000, or more per kilogram, depending on the delivery system. If lunar water ice can be extracted from the polar regolith in sufficient quantities, it could be processed on-site to provide drinking water for astronauts, oxygen for breathing, and through electrolysis, hydrogen and oxygen for use as rocket propellant. A lunar refueling depot, using water mined from the Moon itself, could dramatically reduce the cost of deep space missions by eliminating the need to launch all propellant from Earth's deep gravity well. This concept, known as in situ resource utilization, has become a cornerstone of NASA's long-term planning for both lunar and Mars exploration. This is precisely why the upcoming Artemis missions are targeting the Moon's south polar region. The permanently shadowed craters near the South Pole are prime candidates for water ice extraction, and the nearby elevated crater rims, which receive near constant sunlight, could provide continuous solar power. The combination of water resources in the shadows and energy resources on the sunlit peaks makes the South Polar region uniquely suited for establishing a long-term human presence. Lunar craters are not merely features of Earth's moon. They are a universal phenomenon occurring on every solid body in the solar system that lacks a thick atmosphere and active geological recycling. By studying lunar craters in the depth that our proximity allows, scientists have developed tools and frameworks that they apply to worlds across the solar system. The Moon's craters serve as the interpretive key that unlocks the geological histories of distant planets, moons, and asteroids. Mercury, the innermost planet, bears a surface that at first glance looks remarkably similar to the Moon. It is ancient, heavily cratered, and pockmarked by basins that were later flooded by volcanic plains, much like the lunar Maria. The largest impact structure on Mercury, the Caloris Basin, stretches roughly 1,550 kilometers across and shares many morphological similarities with the Moon's Great Basins. Like the Moon's Imbrium and Orientale, Caloris has concentric ring structures and an ejecta blanket that extends for hundreds of kilometers. Directly opposite Caloris on Mercury's surface lies a region of chaotic, disrupted terrain, widely interpreted as the result of antipodal focusing of seismic waves from the Caloris impact, the same phenomenon proposed for the far side disruption associated with the Moon's Imbrium impact. Mercury's craters have been dated using crater counting techniques calibrated against the lunar standard, providing an estimated chronology for the planet's geological history. Mars, though it possesses a thin atmosphere and has experienced significant volcanic and erosional activity, retains an ancient, heavily cratered surface in its southern hemisphere. Mars also hosts one of the most extraordinary impact structures in the solar system, the Hellas Basin, roughly 2,300 kilometers in diameter and approximately 7 kilometers deep, making it comparable in scale to the Moon's South Pole Aitken Basin. But Martian craters reveal something that lunar craters do not. Many Martian craters, particularly at mid and high latitudes, display lobate ejecta patterns, ejecta blankets that appear to have flowed across the surface, rather than simply ballistically falling. These rampart craters are interpreted as evidence that the impactors struck ground, saturated with subsurface ice or water. When the impact energy melted the ice, the resulting slurry of water and rock flowed outward, like a muddy avalanche, rather than forming the dry, blocky ejecta seen on the Moon. Crater morphology on Mars thus serves as a probe of subsurface water distribution, a connection that scientists could never have made without first understanding how craters form on the dry, waterless Moon. The icy moons of the outer solar system present yet another dimension. Europa, one of Jupiter's 4 large Galilean moons, has a surface made of water ice rather than rock. Its craters look fundamentally different from those on the Moon. Large impacts on Europa produce shallow, flat-floored features with concentric fracture rings, because the relatively warm ice beneath the surface behaves viscously and flows to fill in the crater over time, a process called viscous relaxation. Small craters retain their bowl shapes because they don't penetrate deeply enough to reach the warmer, more ductile ice. By comparing the depth and morphology of European craters to those on the Moon, scientists can infer the thickness and mechanical properties of Europa's ice shell, a crucial question because beneath that shell lies a global ocean of liquid water that is one of the most promising environments for extraterrestrial life in the solar system. Saturn's moon, Mimas, offers a dramatic lesson in cratering at the extreme end of survivability. The crater Herschel, which dominates one hemisphere of Mimas, is 139 kilometers in diameter on a moon that is only 396 kilometers across. The crater-to-body diameter ratio is so extreme that the impact that created Herschel came perilously close to shattering Mimas entirely. Fractures visible on the opposite side of the Moon may have been caused by the focusing of seismic energy from the impact. Herschel's morphology, a classic complex crater with terraced walls, a flat floor, and a central peak, closely matches the predictions of impact physics derived from studying lunar craters. Even small bodies bear the scars of impacts. The asteroid Vesta, which the Dawn spacecraft orbited from 2011 to 2012, has a southern hemisphere dominated by the Rhea Silvia Basin, roughly 505 kilometers in diameter on a body only 525 kilometers across. The impact that created Rhea Silvia excavated enough material from Vesta to create a family of smaller asteroids that orbit the Sun today. Some of these fragments, known as head meteorites for the types of rock they contain, have fallen to Earth, providing samples of Vesta's interior that scientists have analyzed in laboratories. This remarkable chain of evidence, from impact crater to asteroid family to meteorite to laboratory, demonstrates the far-reaching consequences of the kind of cratering process that the Moon first taught us to understand. Comets, too, bear impact scars. When the Deep Impact spacecraft deliberately fired a copper projectile into Comet Tempel 1 in 2005, it created a crater roughly 150 meters across. The excavated material, analyzed by the spacecraft's instruments, revealed the interior composition of the comet, including water ice, organic molecules, and silicate minerals. The experiment was designed using impact physics developed through decades of studying lunar and terrestrial craters, and its results helped scientists understand the role comets may have played in delivering water and organic material to the early Earth. Across all these worlds, the fundamental physics of crater formation is the same. A hypervelocity impact generates a shock wave, excavates a transient cavity, and modifies into a final crater form whose morphology depends on impact, energy, target properties, and gravitational acceleration. The details vary from world to world. Ice behaves differently from rock. Low gravity allows larger craters for a given energy. Atmospheric drag can screen out smaller impactors, but the core process is universal. And we understand that process because we have the Moon, close enough to visit, to sample, and to study in detail that no other world can match. We arrive now at the frontier. The future of lunar crater science is intertwined with the future of human and robotic exploration of the Moon, and that future is unfolding right now. As of February 2026, humanity stands on the threshold of returning to the Moon. NASA's Artemis program, the most ambitious lunar exploration initiative since Apollo, is preparing to send astronauts back to the lunar surface for the first time in over half a century. The Artemis 2 mission, currently scheduled to launch no earlier than March 2026, will carry 4 astronauts on a 10-day journey around the Moon and back. The crew, consisting of NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen, will fly farther from Earth than any human has ever traveled. Glover will be the first person of color, Koch the first woman, and Hansen the first non-American to travel beyond low Earth orbit and around the Moon. Their Space Launch System rocket, standing 32 stories tall and generating approximately 8.8 million pounds of thrust, was rolled out to historic Launch Pad 39B at Kennedy Space Center on January 18, 2026. A wet dress rehearsal was conducted in early February, during which some hydrogen leaks and technical issues were identified and are being addressed. The launch will send the Orion spacecraft on a free return trajectory around the Moon, and the crew will re-enter Earth's atmosphere at approximately 40,000 kilometers per hour, a speed that could set a new record for crewed spaceflight re-entry. Artemis 2 will not land on the Moon. That milestone is reserved for Artemis 3, currently expected to launch no earlier than mid-2027, though as of February 2026, NASA has officially indicated the mission may not occur before 2028 due to heat shield issues identified on the Orion capsule during the Artemis 1 mission and delays in the development of SpaceX's Starship human landing system. When it does occur, Artemis 3 will be extraordinary. 2 astronauts will descend to the lunar surface near the South Pole, a region never before visited by humans. They will spend approximately 6.5 days on the surface, performing at least 2 spacewalks. Among the scientific instruments they will deploy is the Lunar Environment Monitoring Station, a compact, autonomous seismometer suite designed to characterize the structure of the lunar crust and mantle beneath the South Polar region. Every crater those astronauts explore, every rock they collect, every measurement they take will add new data to our understanding of the Moon's history and the bombardment record preserved in its surface. The Artemis program extends well beyond these initial missions. Artemis 4, planned for late 2028, will deliver the International Habitation Module to the Lunar Gateway, a small space station in orbit around the Moon. Subsequent missions will build toward increasingly long surface stays eventually establishing the Artemis Base Camp, sustained human presence near the South Pole. The long-term vision involves missions lasting weeks or even months on the surface, with astronauts conducting field geology, drilling into the regolith to access subsurface ice deposits, and deploying scientific instruments across a wide area. NASA is not alone in returning to the Moon. China's lunar program has achieved remarkable milestones in recent years. The Chang'e 4 mission, which landed on the far side of the Moon in January 2019, was the first spacecraft ever to operate on that previously unexplored terrain. The Chang'e 5 mission, which returned the first fresh lunar samples in over 4 decades in December 2020, provided material from a previously unsampled region of Oceanus Procellarum that proved to be only about 2 billion years old, the youngest lunar basalts yet directly dated. And the Chang'e 6 mission, which returned samples from within the South Pole Aitken Basin on the far side in June 2024, has already produced groundbreaking results on the age of the basin and the volcanic history of the far side. China's future plans include the Chang'e 7 and Chang'e 8 missions, targeting the South Polar region, with the eventual goal of establishing a robotic and potentially crewed research station at the lunar South Pole. India's Chandrayaan program has also contributed important discoveries. The Chandrayaan-1 mission's Moon Mineralogy Mapper produced the first confirmed detections of surface water ice at the lunar poles. The Chandrayaan-3 mission successfully landed a rover near the South Pole in August 2023, making India the 4th country to soft land on the Moon and the first to land near the polar region. Future Chandrayaan missions aim to return samples and continue exploring the South Polar terrain. Private companies are also entering the lunar arena through NASA's Commercial Lunar Payload Services program, which contracts commercial landers to deliver scientific instruments and technology demonstrations to the Moon. In March 2025, Firefly Aerospace's Blue Ghost Mission 1 successfully landed near a volcanic feature within Mare Crisium, carrying a suite of NASA science instruments. These commercial missions are pathfinders, testing the technologies and operational concepts that will support larger, more ambitious endeavors in the years ahead. Every one of these missions, whether crewed or robotic, American, Chinese, Indian, or commercial, contributes to our understanding of lunar craters and the stories they tell. New samples from new locations will provide additional calibration points for crater counting chronology. New seismic data will reveal how impact energy propagates through the Moon's interior. New measurements of permanently shadowed craters will quantify the water ice resources available for future use. And new exploration of the South Polar region, a terrain type that has never been examined up close by human hands, will reveal entirely new insights into the physics and chemistry of some of the most extreme environments in the inner solar system. There remain so many unanswered questions. When exactly did the Great Basins form? Was there truly a concentrated late heavy bombardment, or was the impact rate a long, gradual decline? How much water ice exists in the permanently shadowed regions, and in what forms? What is the full composition of the mysterious dense mass buried beneath the South Pole Aitken Basin? How has the bombardment rate changed over the past billion years, and what does that tell us about the current population of near-Earth objects that could threaten our planet? Can we find evidence of population 3-star material preserved in the oldest lunar rocks? And what secrets do the far side's ancient craters hold that we have only barely begun to glimpse? These questions will drive lunar science for decades to come. And they will be answered, at least in part, by studying craters, those circles that Galileo sketched through his crude telescope in 1609, those pockmarks that ancient observers could see with their naked eyes, those seemingly simple depressions in ancient rock. They are windows into the deepest past of our solar system. Every crater is a timestamp. Every crater is a message. And we are only beginning to learn how to read the full library. So the next time you step outside on a clear night and look up at the moon, take a moment to really see it. See the bright southern highlands with their millions of overlapping scars. See the dark Maria, basaltic oceans frozen in stone, filling the hollows of ancient collisions. See the bright pinprick of Tycho, and imagine the dinosaurs that walked the earth when its impactor struck. See the grand circle of Copernicus, and think of the terraced walls and central peaks hidden within its shadows. Imagine the permanently shadowed craters at the poles, colder than any place you could ever visit, harboring ice that has been waiting there since before the first life appeared on Earth. And imagine the astronauts who will soon stand on that surface again, collecting rocks, deploying instruments, and extending the incredible chain of discovery that began when a Persian astronomer first noted a bright spot in the sky over 1,000 years ago. The moon is close enough to touch almost, just 384,400 kilometers away, less than a light second and a half. Its craters have been staring down at us for as long as there have been eyes to see them. They've been keeping their records patiently, faithfully, for over 4 billion years, and now finally we've learned enough to begin reading them, to begin understanding the story they've been preserving since the solar system was young and violent and new. That story isn't finished. The moon is still accumulating craters, still being struck by small meteoroids every day. Somewhere on the surface right now, a grain of space dust is traveling at 20 kilometers per second toward its final destination, where it will excavate a microscopic crater no larger than a pinhead. And in 1,000,000 years, or 10 million, or 100 million, another large impactor will arrive, carving a new major crater and adding another chapter to the record. The story of impacts is the story of the solar system itself, an ongoing narrative written in stone and ice and light. Thank you for joining me on this journey across 4 billion years of lunar history. We've explored the cataclysmic birth of the moon from the wreckage of a planetary collision. We've traced the physics of impact crater formation from the instant of contact through the long settling of ejecta. We've debated the late heavy bombardment and followed the evidence from Apollo samples to computer simulations to Chinese sample return missions. We've stood at the rim of the South Pole Aitken Basin, the deepest scar in the solar system, and peered into the heart of Tycho, a crater younger than many dinosaur species. We've watched volcanic lava flood the Great Basins and studied the strange asymmetry between the moon's two faces. We've counted craters to build a calendar of the solar system. We've discovered water ice in the eternal shadows of the poles and imagined the outposts that may one day harvest it. And we've looked out across the solar system and seen the same cratering process at work on every solid world, from sun-scorched Mercury to frozen Europa. The craters of the moon are not just marks on a distant surface. They are a record of everything that has happened in the inner solar system since its formation. They tell us where the planets came from, how they evolved, what struck them, and when. They tell us about the violence that shaped our cosmic neighborhood and about the quieter eons that followed. And they tell us something about ourselves, that we are a species capable of looking up at a pockmarked rock in the sky and seeing in its scars the entire history of our world. If you enjoyed this deep exploration, a like and a subscribe would help the channel grow and would allow me to keep making these journeys into the cosmos. Until next time, keep looking up. The moon is always there, patient and luminous, its craters waiting to be seen. Sleep well tonight, knowing that those ancient scars are keeping watch overhead, silent witnesses to 4.5 billion years of cosmic history, and that every one of them has a story to tell. Good night.